sir. Welcome, sir. Dr. Sudhir Das, sir, is presently working as an assistant professor in Department of Computer Science and Engineering, NIT Warangal. He is awarded PhD from the Department of Computer Science and Engineering at NIT Durgapur. Dr. Das has 18 years rich experience in teaching along with 9 years experience in research with quality educator sector. He has published around 50 papers in the referred journals and conferences and scored 1,000 plus citations. He has research publications in prestigious journal like Applied Soft Computing, Neural Computing, and Applications, International Journal of Fuzzy System, Journal of Ambient Intelligent and Humanized Computing, Soft Computing, Journal of Intelligent and Fuzzy Systems. He is working as active reviewer in many reported journals and conferences, achieved three conferences, Best Paper awarded in CSU 2014, Beijing, FICTA 2015, Durgapur, and FRBS 2018, Kolkata. Dr. Das is a well-known resource person in the field of universal human values, UHV, which is required to nurture the human minds in order to bring the feelings of happiness in ourselves, our family member, and our society at the larger perspective. He has delivered a number of talks in universal human values in various workshops throughout the India. He has organized a number of faculty development programs, FDPs, and conferences. Moreover, he has chaired many sessions in the prestigious conferences. Uh, he has been delivered talks as invited speakers in many FDPs, seminars, and conferences. His research interests include fuzzy system, hybridized fuzzy subset, multi-criteria decision making, robust optimal solution using soft computing. AI, evolutionary computation, and machine learning. Welcome, sir.
Yeah, thank you, sir, for this nice and brief introduction.
Yes, sir.
So really, it's a great opportunity for me to share my thoughts on this platform, on this AI applications for engineers. Really, I am thankful to the organizers of this FDP for inviting me to share my thoughts here.
Welcome, sir.
Now, yeah. So now I will start my session. Wait 1 minute. And so can anyone confirm, please, my screen is visible or not?
Visible, sir.
Okay, thank you. So today, our topic of discussion, this is fuzzy logic and applications. So this is the presentation outline of our today's discussion. And so I would like to request my participants so that they can ask me queries at any time. They can interrupt me at any time during my presentation. Also, feel free to raise your questions at the end of the session, whatever you feel like better. But I will be happy if you interrupt me during my sessions also. Yes, so initially, so I will tell regarding some introduction to fuzzy set and fuzzy logic. Then gradually I'll move to this fuzzy logic controller. Then we'll try to find out how to design a complete fuzzy logic based system. Finally, so we'll explain this Mamdani approach, that is the application area in mobile robot. So what is fuzzy? So actually, once we need to say that what is fuzzy. So if we find out online dictionary, so what perhaps we will get, so that fuzzy means something like confused or not expressed clearly. So then I think participants may be wondering that if fuzzy means something that is arising some confusion or that is not expressed clearly, then what is the need to discuss this topic in such FDP? Actually, yes. So what is the fuzzy logic? Actually, fuzzy logic is built to deal with this kind of situations, which is confused and which is not expressed clearly. Fuzzy logic or fuzzy set itself is not fuzzy. Okay, so it is used. Okay, it has been developed to deal with the situations, which are the situations where it will be much more confused, or which where the informations are not there, precise informations are not available, complete informations are not available, or we are unable to define the situations quite clearly. So that is the need of that we need to discuss, or we need to study this fuzzy set concept. Yes. So as I was telling that, yes, so what is the need that we are wondering that why should we deal with the things that are inherently vague or inherently fuzzy in nature? You know, if I say that one statement that today, the most certain, today, yes, in our real life today, the most certain statement is the uncertainty. The most certain thing is the uncertainty one. So can you imagine something surrounding us which is very much precisely known, which is very much well defined to us? So for just year backs, only 1 or 2 year back, starting from 2019 December, we faced so much challenges with this corona, COVID-19. And to till today, we have so much information regarding COVID-19. But again, we are unable to, I think, find out which is the suitable or which is the appropriate, which is the most well adapted techniques to deal with this novel COVID-19. Because, today China is suffering a lot. Day by day, cases are rising. So many cases, almost all hospitals are full. They are in a very much pathetic situations. Right now, we are a little bit in comfortable situations. But what are the things regarding COVID-19? Whatever we know, that is not enough. Whatever the information we have regarding this COVID-19, again, that is incomplete. That is imprecise. Not only on COVID-19. See something, find something surrounding you. You will find out that information regarding that things or regarding that incident or regarding that particular matter, you don't have either the complete informations. Some informations may be missing, something is not precisely defined, and definitely something is there which are not available there. That means almost each and every day we need to deal with this uncertain kind of situations. We cannot avoid that. So how to deal, how to work uh, using these uncertain kind of situations? Yes, then to work or to manage this uncertainty, so fuzzy set or the idea of fuzzy logic will help you. And that is the need of this fuzzy set or fuzzy logic. So often we say some terms that the boy is intelligent, the building is very tall, the garden is beautiful, that place is very much far. Now, once we say that the boy is intelligent, what do you mean by that? What is the definition of intelligent? The definition of intelligent it may be differ with me, whatever I am thinking like intelligent, and also your another coordinator, Dr. Sanjay Kumar Panda, may feel that intelligent is something else. That means what is happening? So the concept of intelligent is differing from person to person. Like once I am telling that building is very tall. So again, the same thing. The idea of tall, how much length or height the building should have to define it tall. Again, that perception may vary from person to person. Then what is the situation? See that exactly what is happening here. So that means we don't have very much precise meaning regarding the intelligent, regarding a very tall, beautiful, very much far. We don't have a very much precise meaning. Fine, it may vary from person to person. Then how you will deal with this kind of situations? I am telling the boy is little bit intelligent. The boy is more intelligent. The girl is again much more intelligent. What I mean to say, how you will numerically represent these terms, these linguistic terms. It is very difficult. Now let us see. So these are the example of imprecise terms. And the thing is that we cannot ignore this kind of imprecise terms. In our day-to-day life, we need to work with these imprecise terms. And again, one important example I can tell that yes. So now consider some situation where you want to buy a gift. And suppose you plan to buy the gift of rupees 200. So your budget is rupees 200. Now tell me. So you will purchase the gift once it is exactly rupees 200, or also you should purchase the gift if it is little bit more than 200, little bit less than 200. What it will do? Yes, the situation is that so it is not exactly 200. No, it can be 190 to 210, 180 to 225, like that. Now see the situations here. See what is where is the uncertainty? See, so yes, so that means 200. Once I am planning to purchase a gift for my friend of rupees 200, so 200 is actually something like about to 200. Yes, about to 200. See the term about 200, and ultimately here we are getting the introduction of this imprecision and this uncertainty. Uncertainty means here I want to make it very simple. I will try to make it. Uncertainty means either incomplete or imprecise. That I mean to say that is the uncertain kind of things. Again, see another situation. So if I say that 75% possibility is there that today there will be some rain in Warangal. So what does it mean? I am telling 75% possibility of rain today. What does it mean? Maybe someone will feel okay. So out of 24 hours, 75%, that means for 18 hours, it will be raining. Remaining 6 hours, no rain. Maybe someone may perceive in that sense. Some others may perceive that yes, in Warangal, what is the total region? 75% of the region, there will be rain. Remaining 25%, no rain. And someone may feel that in the last 100 years, on 70% occasions or 70% days, it was rained. Now see what is happening. So I am telling something, and the idea or the perception is differing from person to person. So this clearly we can find out. So once we say something in our day-to-day life, all these terms are imprecise terms only. Still, I can remember once I felt some power cut in my quarters in a night Warangal. Then immediately I called Dr. Sanjay Kumar Panda. I was telling, okay, sir, I will come some within 5 minutes. It may be less than or little bit more than 5 minutes. No, see, again I was telling the term that was the imprecise term. So that means we cannot avoid these imprecise terms. In our daily life, we will get so many examples of imprecise terms. Then the problem is that how you will work with this imprecision, how you will work with this incompleteness. You don't need to worry. So here, concept of fuzzy sets and fuzzy logic is there that are going to help us for this situation. Yes, so can we ignore the imprecise terms? We cannot ignore. We cannot ignore. Simply, one more example. A doctor may say, if too much temperature or too much fever or too much pain is there, take one tablet. Now see, too much temperature, too much pain, that means again, the pain, whatever I can adapt, I can feel, and the pain some others can feel again, can feel, so that may be the different. Process controller may say, if temperature is high, then turn on AC. High means what? How much it is high? So all these things, I think, we are getting that terms are imprecise in nature, and simply we cannot ignore these imprecise terms. Yes. So there is a scope of this fuzzy statement, and we need to reason with these uncertain or imprecise statements to come to a conclusion. We are finding so much imprecise terms. Should we leave it? Once something is imprecise, we should stop our work. We should postpone our work. We will simply sitting idle. No work. We cannot do that. That means we need to learn to reason with uncertainty and impreciseness. And that is the scope of the fuzzy set or fuzzy logic. As I was telling, fuzzy set or fuzzy logic itself not fuzzy, but it has been developed to deal with the fuzzy nature. So that is the concept for fuzzy logic. Now, you may be wondering that once I am telling regarding this concept of fuzzy set or uncertainty, so we have some well-known idea, very much stronger mathematical concept of probability, where easily we can manage the uncertainty. So uncertainty can be managed with probability. Then where is the need of the fuzzy set? Later I will tell you where is the difference between the probability and fuzzy set. So if you look closely, then you can feel that type of uncertainty that probability manages, that is the stochastic uncertainty. You know, stochastic uncertainty means what kind of uncertainty? That is the uncertainty that over time. All of you know what is the definition. This is the definition I have written for the probability, not going through that. So probability means basically stochastic uncertainty. Okay, so that is the uncertainty over time. But once you are feeling regarding the fuzzy set, this is not stochastic ambiguity. There is no stochastic uncertainty kind of things in the concept of fuzzy set. It is totally different. Here it has inherent vagueness in the definition of the term itself. Tall, see that. Tall, can I say tall, very tall, less tall, medium tall? This is related to stochastic uncertainty, that is related with time. Or I will tell this is some inherent uncertainty, inherent some vagueness is associated with this linguistic term that is known as tall. As I was telling, the perception of tall that may be different from person to person. See, where is the difference? Uncertainty with the fuzzy sets and uncertainty with the probability. Obviously, we can manage the uncertainty with probability, but those uncertainties should belong to the category of this stochastic uncertainty. If those are some another kind of uncertainty, we should take help of this fuzzy set or fuzzy logic to manage this. Yes. So how do we handle this ambiguity? Now let us move into the concept of fuzzy set little bit. I should say Professor Lofty Zadeh, you know. So Professor Lofty Zadeh from University of California, Berkeley University, sir introduced the concept of fuzzy set in 1965. And today we are unfortunate. I feel sad to convey that sir has left us for heaven in 2017. So, but what the foundation sir has laid, what is the things sir has given to us? Obviously, we feel that that's all our God-gifted kind of things, because this uncertainty kind of things would not have been possible without the introduction of this concept of fuzzy set by our Honorable Professor Lofty Zadeh sir. Here I will tell you something that how sir told the concept of fuzzy set. Let us say. So consider a set that is about to 10. Okay, we are considering a set about to 10, that is A. Obviously, once the set is about to 10, then 10 belongs to the set A. No doubt about that. Okay. Now, this line 9 that may belongs to set A. See that with the degree of belongingness 0.9. See the term, what I am writing. The degree of belongingness 9 may belongs to A with the degree of belongingness 0.9. Also 11 may belongs to A where the degree of belongingness may be also 0.9. 8 and 12, that also maybe belongs to A. But here, the degree of belongingness is 0.7. See, so this is that 10. So here I am considering degree of belongingness for 10 is 1. See, 9. I am considering degree of belongingness of 9 to the set about to 10, that is 0.9. That is 0.9. Yes, that is considering that is 0.9. Here again I am considering one number 11, and again I am considering the degree of belongingness of 11 to the set about to 10 is 0.9. See what is the situations are going on. If I take another number 8, here I take another number 12, then maybe here degree of belongingness maybe it is 0.7. Here the degree of belongingness also it may be 0.7 like that. See here. The set is about to 10. That means once it is 10, it is degree of belongingness I may consider that is 1. Once it is 9, degree of belongingness little bit less, that is 0.9. Once it is 8, degree of belongingness is more or less, that is 0.7. Actually, whatever I am telling in terms of degree of belongingness, this is nothing but the membership degree. That are important. That is an important idea of fuzzy set. Membership degree. In simple set, so that may be an simple set. 8, 9, 10, 11, 12. Simple set, that may be 8. So, in the concept of a set, what we normally say? An element belongs to the set or does not belongs to the set. If an element belongs to the set, what is the characteristics function value? That is 1. It does not belongs to the set means it is 0. So simply see that once we are writing simply a set, so we can write the set like suppose 8, 9, 10, 11, 12, that is a set. Here 8, 9, 10, 11, 12 for each and every element. Here what I can tell? Characteristics function value is 1. Because these elements belongs to the set. Two concepts. One element can belongs to the set or cannot belongs to the set. If belongs to the set, characteristics function value is 1. That means I can write, yes, 8, it is 1, 9, it is also 1, 10, it is also 1, 11, it is also 1, 12, it is also 1. Since all are 1, that's why we omit this term 1. Okay. But in case of fuzzy set, what is happening? In case of fuzzy set, along with each and every element, the concept of membership grades also will be there. So 8, what is the membership grade? 0.7. 9, what is the membership grade? 0.9. 10, what is the membership grade? This is 1. 11, what is the membership grade? This is 9, and so on. See that. This is the concept or definition simply or an example of a fuzzy set. With each and every element, one membership grade should be added. What is actually the membership grade? As we have written, this is the degree of belongingness. Or I can say, the degree of involvement of this element 8 to the set A is 0.7. Degree of contribution of element 8 to the set A, it is 0.7. So this is the membership rate. How much it belongs, how much it has the involvement, how much it contributes to the set, that is the membership degree or membership grade. Here you can see that whatever the membership grade I am writing, I am not writing randomly. This is a specific, there is a specific logic, specific idea how to find out the membership grade of each and every element. Later I will discuss at right time. But the membership grade, whatever I am writing, this is not a random. You can check membership grade of 9 once I am writing 0.9. Can I write membership grade of 8? This is 0.95 or something else. Can I write? Or can I write membership grade of 8 is 0.9 and membership grade of 9 is 0.8? Can I write it? So as per my definition of this fuzzy set, about to A, about to 10, that is A. So I cannot write that. That means which is much more closer to 10, membership grade will be more. Which is less closer to 10, membership grade will be less. So that's the concept behind that. See, yes. So here it is written. So in this format also we can write the concept of this fuzzy set. See that. All the elements are there. So these are the elements of the set, and these are the membership grade associated with each and every element. Also, we can write in this manner. So fuzzy set, some elements will be there. Along with the elements, we need to mention the membership grade. In case of a simple set, traditional set, classical set, no need to mention the membership grade. Why? Because it is assumed that membership grade of each and every element in a classical set be 1 only. That's why no need to mention that. So later again I will come to the definition, but I hope that you are getting some idea regarding the fuzzy set. Yes, so sir, that is the Professor Lokti. Yes. So as I said, that Sir has laid the mathematical foundation for fuzzy set theory, and by extending the fuzzy set theory, Sir has introduced the concept of fuzzy logic. Now, what was the things going on in Sir's mind once Sir has developed the concept of fuzzy logic from the concept of fuzzy set. Already we know the concept of fuzzy set. Next, we will try to explore the concept of fuzzy logic also. Sir has observed that conventional computer logic cannot manipulate data that represented subjective or vague ideas. So he created the fuzzy logic concept to allow computers to deal with those kind of situations. And you will be happy to know that the concept of fuzzy reasoning that I will discuss later is very much similar to the process of human reasoning only. How we are human beings, how we can think, the fuzzy logic is also enabled to think in similar kind of nature. Yes. Now, since we know a little bit the concept of fuzzy set, so we are moving to this fuzzy logic. Yes. As I was telling, computational paradigm that is based on how human think, So how human think, fuzzy logic will try to think in the similar manner. Now, if you can see how human can think, once I'm thinking something, once I'm in my mind, I'm trying to perceive something, what actually I am doing. Our human brain, so once we take some information from the outside, from our surrounding us, information may be imprecise information. Now tell me, we are taking some imprecise information surrounding us from the nature. Okay, surrounding us, some natures are there. We are taking the information in an imprecise manner. Now tell me. But once you will respond, can you respond in imprecise manner, or always you respond in precise manner? See, so that is the capability of the human brain. We can take the things which are in uncertain kind of situations. We adapt, we perceive the things, we reason with the things. But once we respond, obviously we respond with some precise actions. So that is very much important. That means the fuzzy logic concept also should carry the similar kind of task. See the importance between fuzzy logic and human brain. Fuzzy logic also will try to get the things, so which are imprecise in nature. But once fuzzy logic will process of all those things, and in return, it will try to respond, conclude something. Obviously, the conclusion should be some precise actions. Similar. So now we'll try to find out that we'll try to explore that how fuzzy logic is doing exactly the similar thing, how the human brains or we, the human beings, are doing. So one important thing is that so human brain can reason with uncertainties, vagueness, and judgments. And see, at the same time, computer can only manipulate precise valuations. See that important term. Human brain can reason with uncertainties, vagueness. Okay, but computer can only manipulate precise valuations. See the situations. Then, if we can combine these two things, that will be the wonderful kind of, I think, wonderful kind of things or wonderful kind of invention. Yes, that is the fuzzy logic. Fuzzy logic is an attempt to combine these two techniques. So, uncertain nature of human brains as well as the computing power of computers. So these two things once we are adapting, and as a result, fuzzy logic is coming into picture. So now you can feel that how much powerful the fuzzy logic be. Yes. So as I was telling, that fuzzy logic, that is a precise problem solving methodology. Precise, you cannot say fuzzy logic is fuzzy only. No, no. Fuzzy logic is a precise problem solving methodology. And fuzzy logic differs this from the classical logic. And as you said already, I told that in the classical set, two things are there, either 0 or 1. In the classical set, only two numbers, either 0 or it is 1. That means an element may belongs to the set, it is 1. An element does not belongs to the set, it is 0. There is nothing in between 0 and 1 in classical set, in a classical logic. We can say 0 means false, 1 means true. But fuzzy logic differs from the classical logic. You know, fuzzy membership grade, whatever we have seen right now, so those may take the values in between 0 and 1 also. Those may take the values 0.1, 0.2, 0.3, dot, dot, 0.9. So that is in between 0 and 1 also. Yes. So fuzzy logic, that means differ from the classical logic in the statements that are no longer black, white, true or false, on off. In fuzzy logic, something is there which is in between true and false, in between 0 and 1, in between on and off. So that is the important idea behind this fuzzy logic. Now here I'll try to tell that what are the various applications of fuzzy logic very quickly. You know, so this introduction of fuzzy logic to the engineering world, we witnessed it around in 1990s. Basically started from 1985. You know, so even so, whatever today, most emerging technologies today is the age once we are living, that is AI, that is dealt with data science and machine learning. But you know, there is a very much close relations of this fuzzy logic all with the AI, data science and machine learning based approaches. You can find out that we are using fuzzy logic so to manage the uncertainties even in machine learning, even in AI and data science. Many more research works are going on in these directions. Now, fuzzy logic has a huge importance for this low-cost microcontrollers. You know, microcontrollers, once we say that term, you will feel what is the importance of these low-cost microcontrollers. Each and every device, AI-enabled device, almost we are using this concept of microcontrollers. And it is the concept of fuzzy logic is very much suitable once you are discussing with a low-cost microcontrollers. Intel Corporation, they embedded the concept of fuzzy logic, and ultimately they worked with this microcomputer division fuzzy logic based operation. And many other you see here you will find out many other applications of fuzzy logics that we can use the fuzzy logic for handwriting recognition, hand printed character recognition, voice recognition, for stock trading portfolio based on fuzzy logic, and many other applications of fuzzy logic you will find out. Simply since it is used to manage the uncertainty, so we cannot deny the existence of fuzzy logic. Fuzzy logic is useful almost each and everywhere where the concept of uncertainty is there. So NASA, they have started, they use the concept of fuzzy logic for automated space docking. That was a very much important kind of things. So that fuzzy control system they developed that greatly reduced the fuel consumptions. Once with this automated space docking or aircraft, this fuel consumption is very much important. And NASA studied and used that concept for that purpose. For Canon, also they developed, all the, not only Canon, whatever we are in our today, all our smart devices, we are finding some auto-focusing camera. So much, I think, high capabilities cameras. So each and everything here, you will find out that once it is auto-focusing camera, obviously the concept of fuzzy set should be there inside it. Anyway, so now almost we are getting that what is the idea of fuzzy sets and fuzzy logic, and what is the importance of fuzzy logic, and what are the recent applicability areas of this concept of fuzzy logic and fuzzy sets. So here that was the history of development of fuzzy sets. As I told that in 1965, Sir Jadek told, they just discussed this concept of fuzzy sets. And around that, I told 1985, researchers and Bell Laboratories, they started this fuzzy logic concept and developed some fuzzy logic based chips. Yeah. So now one thing again I should mention here, that exactly again one important paradigm we will discuss, that how the concept of uncertainty is coming once we are solving some problem. See the situations. So we are taking some problem with us. Okay, so problem is a huge problem. Today, all of you are working a little bit on this big data. Huge so volume of data is there. And the problem is very much high, very much huge volume of data, huge volume of informations are there in our problem. So what normally we are doing? So normally we are trying to, once we are going to solve a problem, we are trying to simplify a complex problem. See that once you will run for simplifying a complex problem, easily you can feel that what you may lose. Yes, simplification of complex problem, that will lead to the loss of information. And we need to simplify the problems. Otherwise, we need to do, those who are working with AI, machine learning, data science, a lot more pre-processings we need to do. Once you are doing the pre-processing, maybe there is a chance that you will lose some information. Now, obviously, once you lose some information, so that will raise the uncertainty in your problem. You cannot avoid that. So that is the simplest idea. So that means, so in that sense also, once you have with you a complete data set from all sides, but again, for the purpose of your computation, you are simplifying the complex problem, complex data set. Again, the same thing is appearing. You are losing some informations, and that is leading us to some uncertainty, where you need to use the concept of fuzzy set or fuzzy logic to deal with that. Here again, some examples I have given. If I say, when you have joined to this FDP, someone says, sir, almost right time. Someone will say, sir, little bit late. Someone will say, sir, little bit earlier. That means C. Whatever the terms you are telling, again, all of the imprecise terms, that means if you want to use these terms in your computations, you cannot avoid fuzzy set. You need to use the fuzzy set to use to deal with these terms. This is the significance of this fuzzy logic. It enables us to model human reasoning process at a higher level. This is used to model the real life situations. It is used as a tool for finding solutions to AI-based problem, as I was telling. In AI-based problem, you will find out in many places the concept of uncertainty may appear, that easily you can adapt the concept of fuzzy set to come out from this concept of uncertainty. So this concept of fuzzy set, creep set, already I told that fuzzy set, fuzzy logic, this is the extension of fuzzy set. Creep set means either true or false. And fuzzy set means it has true or false, means it is 1 or 0. But in case of fuzzy set, it is also there it has an existence in between true and false also, in between 1 and 0 also. See the Krebs logic. See the simplest example of Krebs logic and fuzzy logic. See here. If you consider that 0 to 80 degree Fahrenheit, this is not hot. If temperature greater than 80, that is hot. If temperature less than 80, that is not hot. See the situations. Here hot means I will say it is 1, not hot means I will tell it is 0 or false. Now you tell me, if the temperature is 79.9, will you say it is not hot? See the situation. Temperature is 79.9. But as per the applicability, as per the definition of the Krebs logic, once it is 79.9, then we should say it is not hot. But actually, in reality, it is hot only. That means you don't have the scope to define temperatures much more accurately in the framework of this Krebs set. Yes. The membership functions of a Krebs logic fails to distinguish between the members of the same set. Also, to detect the little difference among the members of different set, as I was telling. Temperature 100, it is hot. 80.1, it is hot. Suddenly, once I am telling 79.9, it is not hot. This is as per the idea of this Krebs logic. Obviously, so Krebs logic will not be useful to deal or to manage with the real life scenario. So we need something else. We need the concept of fuzzy set or fuzzy logic. Now it's the time to discuss in detail. So what is the difference between fuzzy set and probability? Now almost you know the concept of fuzzy set and probability. So now let us see to explore the difference between these two. I will tell you a very simple example. Okay, as you know that fuzzy set and probability, fuzzy membership grade and probability both lies in between 0 and 1. But fuzzy membership grade is not equal to the probability. Now let us see. Suppose I will give you 100 glass of water. Okay, 100 glass of water I will give you. And then I will tell you that drinkability of probability or probability of drinkability is 0.95. And at the second statements I need to say, membership grade, fuzzy membership grade of drinkability, it is 0.95. Again, I am repeating. I will take 100 glass of water. Two statements I am telling. Probability of drinkability of water on all those 100 glasses is 0.95. First statement. Second statement I am telling. Membership grade of drinkability of water on all those 100 glasses, 0.95. Now tell me, which glasses you will prefer based on the concept of probability or based on the concept of fuzzy set? See the situations. If you are unfortunate enough and if you adopt the concept of probability to select a glass of water for you, which will be much more safe for you, drinkable for you, and if you are unfortunate, then maybe you need to take the glass of water which is not pure at all, if you select the concept of probability. Because once I am telling the concept of probability, that means 95 glasses of water is fully drinkable and remaining 5 glasses of water are not drinkable at all. And if you are unlucky, if you are unfortunate enough, you will select that glass only which is not drinkable. So this is the problem with this probability. But in case of fuzzy set, what will happen? All of the glasses, 100 out of 100, purity level or drinkability level, membership grade of drinkability level is 0.95. That means all of the glasses, 100 out of 100 glasses of water are almost drinkable. 0.95 means almost drinkable. That means if you are unfortunate enough, again, there is no issue. You can randomly select any glass and that will be safe for your health. So that is the math. That is the thing that I think fuzzy set is very much important rather than probability. But we cannot say, if you ask me, sir, which will survive, which will vanish, I will say, I will must answer that fuzzy set and probability has their different perspective. Both they will survive. Fuzzy set and probability, both they will survive years to come because they have some different perspectives for the different problems. Yes. So probability means the water is drinkable or not. But fuzzy set means it is more or less drinkable. Yes. So see. So this kind of concept, more or less drinkable. But here in probability, it will give you that liquid is either drinkable or not drinkable like that. Now, these are some real life applications. Once we are discussing the concept of fuzzy set or fuzzy logic, washing machines, air conditioners. Today, it is the fuzzy washing machines. Today almost we have intelligent or fuzzy washing machines. That means once we will give that, I think, cloths inside that washing machine and powder washing powder you are giving, then ultimately how much time it will take, okay, to make your clothes clean, automatically things will be determined. How it can do that? How it can do that? Obviously, intelligent enough. So concept of fuzzy sets are embedded in the washing machines. This is known as the fuzzy washing machines. So almost all the sectors, either it may be household product or it may be commercial systems, each and every places we may get an applications of this fuzzy logic. So already I have told you the fundamentals of a set, so that I'll once again I'll not repeat. So set means the collection of elements which are not repetitive in nature. So as I said, you can recall that in the concept of creep set, so that is the characteristics function. That means a member, a number may belongs to the set, then it is 1, may not belongs to the set, that means 0. So this is the characteristics function value for a fuzzy set. Definition mathematical for a creep set. If x not belongs to A, it is 0. If x belongs to A, it is 1. So there is nothing in between 0 and 1. Now see. So this is the classical set, either 0 or 1. Now this is the fuzzy set. See. This is the definition of the fuzzy set. So mu Ax, that means this is the membership grade. What is x? X belongs to the elements. X means the element. So as in the earlier example I have shown you that in the fuzzy set, with each and every element, there will be the concept of membership grade. Membership grade means it is nothing but degree of belongingness of an element to the set, or degree of involvement of an element to the set. We define with this membership grade. So this is the definition for this fuzzy set. So you can note it. So this is the definitions for this fuzzy set. This is the element. This is the membership grade. Yes. Now, in this next 1 hour, so we will move inside this, how to design a complete fuzzy system. We want to design a complete fuzzy system, fuzzy-based system. Now, let's move towards this. So, yes, so we want to define a fuzzy logic-based system. So, again, the same thing I should repeat. Fuzzy logic is not the logic that is fuzzy, but this is the logic that is used to describe the concept of fuzziness. Okay. Yes. So this applications of fuzzy logic, see. So this concept of this fuzzy theory can be applied in many applications. So that fuzzy reasoning, fuzzy clustering, fuzzy programming. Actually, all these are some different directions of fuzzy logic. Since today, this session is entirely on fuzzy logic, so I will try to restrict myself on this fuzzy reasoning part only. Later, if I get some time or if I get any scope, obviously we will discuss these other two objectives. Today, our task is entirely to focus on this fuzzy reasoning. Fuzzy reasoning is also called as fuzzy logic controller. See, very much important one, fuzzy logic controller. What about the applications of fuzzy logic? You will see each and every application contains this fuzzy logic controller. even microcontroller that contains the fuzzy logic controller. We can say this fuzzy logic controller, these are the special kind of expert systems. Rather, I should say fuzzy expert systems. So once I tell the term expert systems, I feel that you are thinking that something in the systems it is there which will give us some expert ideas or expert result. Obviously, it is very much like that only. So in this fuzzy logic controller, okay, so that has a knowledge base. Knowledge base means what? So we normally consider knowledge base is enriched with some knowledge. Now here, the knowledge will express in using some propositions, using some rule. If this, then that. If clothes are more dirty, then washing machine should take more time. Like that. If number of clothes are less, dirtiness is less, washing machine should take less time. See, so these are the rules normally that we keep inside the knowledge base. And these rules are known as these fuzzy inference rules. And also, so once you that, so see that. So what I'm telling, that in fuzzy logic controller, you have some knowledge base. And in the knowledge base, some kinds of knowledges are there. And knowledges are represented using this if then that kind of rules, fuzzy inference rules. So once some rules, some knowledges are there in the knowledge base, that means something should be there who will work or who will fire, who will use the knowledge base as per demand. So that is the fuzzy inference engine. Fuzzy inference engine will fire the rules or will fire the knowledges from the knowledge base to do the intended task for the system. Inference engine. So inference engine will be associated with this knowledge base, and main task of inference engine is that it will fire that particular rules which is suitable to that particular system. So that is the necessity for this fuzzy inference engine. Yes. We use fuzzy logic controller where an exact mathematical formulation of the problem is not possible or very difficult. See the situation. Where you will use this fuzzy logic controller, almost in all the problems where uncertainty is there is no precisely defined analytical mathematical model for that. No chance. There is no precisely defined mathematical model for a particular problem. Then what to do? If it is the precisely defined mathematical model, no need to use fuzzy set, go for probability, other things, it will be okay. But once it is not like that, then it is very much difficult, and you need to use the concept of fuzzy logic controller. So how these difficulties are coming? So due to the non-linearities, how these difficulty in the problems are coming? Non-linearities, because you are unable to define that variables in a linear manner, in a linear fashion. Once it is linear, it's okay. It is easier. You can adapt any mathematical ideas from, I think, linear programming model is there, the very much important concept of mathematics or person research. But once it is of non-linear, then how to manage it? Time varying in nature, like COVID-19. So each and every time it is mutating, and ultimately it is making us full. Whatever we are doing in the next month, after some time, we are finding it has changed its nature, and it has made us full. Like that. Time varying in nature. Large unpredictable environmental disturbances. Something is there which cannot predict. So what to do that? If you are working with these kind of problems, then obviously you can easily feel, you can perceive that exact mathematical model is not possible. Better to work with this fuzzy logic controller based system. So this is a quick diagram of this, or very brief or precise diagram of this fuzzy logic controller. So that although FLC, fuzzy logic controller will work with imprecise terms. But here I am telling you precise terms, that here I have modeled the fuzzy logic controller in precise manner. That means, okay, each and every modules of this fuzzy logic controller are given here. See, fuzzy rule base number one module. As I told, some set of rules, that is the knowledge base. Some set of rules should be there in the fuzzy knowledge base, fuzzy rule base. Next, inference engine. This is associated with this fuzzy rule base. The task of fuzzy inference engine is to explore the rules, to fire the rules. I will say, later I will show you how to fire the rules in the fuzzy rule base using fuzzy inference engine, which are necessary. Because, in fuzzy rule base, many rules may be there. Suppose 20 rules, not only 20, 100,000 number of rules are there. Is it necessary to explore, to fire, to evaluate each and every thousands rules for your system? No. Your system may be useful for a particular subset of rules. How to fire those set of rules? You need to fire using the concept of fuzzy inference engine only. Next, fuzzification module, very much important one. Whatever the information I am getting from my surrounding, is it fuzzy? Creeps only. You are entering something in washing machine. Is it fuzzy? Your clothes are fuzzy? Or whatever the things harp you are giving, all these are fuzzy. Nothing is fuzzy. So once you are giving some input from the system, those are Cripps values. 10 number of clothes. Some amount of this powder, washing powder. All these are quite given very specifically, Cripps in nature. Inputs are never fuzzy. Inputs are Cripps only. Then, so based on the Cripps input, they will initiate some conditions. And those conditions need to be converted into fuzzy logics, simply into fuzzy membership grades. See that once again I am telling. So we are supplying some Cripps input to the system, and those Cripps input will be converted into corresponding actions, and each and every actions will be associated with some membership grades. So fuzzification, mainly fuzzification module, the task is there to convert Cripps set into fuzzy set. Simply you can see like that. Fuzzification module. We have the Cripps input. It will generate the fuzzy input for that. From the Cripps set, it is generating the fuzzy set. Okay, next. What is this defuzzification module? That is our module number 4. So in your washing machine, clothes are given, washing powder is given, everything liquid is given, everything is given. Then it is determining the time. Now tell me, the time it will determine, or the things it will determine, that will be fuzzy or that will be Cripps in nature. It will take 40 minutes time. It will take 1 hour, 2 minutes time, like that. All these are Cripps in nature, the output. That means whatever the job, your task, fuzzy controller is doing, at the end of the day, the fuzzy controller should provide some Cripps output. This is the task of defuzzification module. It will convert the fuzzy membership grade into some Cripps value, and corresponding actions will be generated based on that Cripps membership value. That means what will be the movement of your tab, or what will be the movement, how it will work, your washing machine will work, like that. So defuzzification module. So it is from converting fuzzy membership grade into, or fuzzy set to Cripps set. So this is our, we can say this is mainly our fuzzy system, fuzzy logic controller, but this is our Cripps system. This side system, so we can say these are our Cripps system. We are providing some Cripps input, as well as once the task of FLC is over, as a result, we are getting the Cripps output. So that is very much important. So as I told, so this is the fuzzy logic controller. Fuzzy logic controller consists of these four modules: fuzzy rule-based inference engine, fuzzification module, and defuzzification module. Yes, all these things I told, the steps of this fuzzy logic controller, that it will take some input. I told the steps for fuzzification. Okay, what is fuzzification? Then what is the inference engine? To evaluate the control rules. Even inference engine is meant for to evaluate the control rules stored in the fuzzy rule base. Defuzzification, as I told. So the fuzzy set is converted into Cripps value using this defuzzification module. See, this is the example of fuzzy logic controller washing machine. See here. Normally we say linguistic inputs. That means what is the type of the dart, dirtiness of the clothes. Once we are giving it, so that is the Cripps input. Fuzzification converted into fuzzy set, fuzzy membership grade. Then this is mainly the fuzzy logic controller. Okay, so here based on the rule base, it is in consultation with the fuzzy inference engine. So it is producing some again membership value, and those membership values are defuzzified. Means again it will generate the Cripps input. Ultimately, it will give you the washing time. So this is the working principle for this washing machine. Now you can see, I think you are waiting to find out, sir, what is the example of some rules, what we can use for the washing machine. See, this is the one rule. If dirtiness of clothes is large, type of dirt is greasy, then wash time is very long. So this is one kind of rules. Okay. A dirtiness of clothes is medium, type of dirt is greasy, wash time is long, like that. So these all are the rules you can consider, which are stored in this knowledge base of this washing machine or fuzzy logic controller. Now, once we are discussing the fuzzy logic controller, there are mainly two approaches. One is the Mamdani approach based on the and second one is the Takagi-Sugeno approach. Two approaches are there. Okay, to explain the concept of this fuzzy logic controller or how this fuzzy logic controller works, mainly these two approaches we need to study to know it. Today our task is that we'll go for this Mamdani approach in detail. And Takagi-Sugeno approach perhaps we may not discuss today. Now in this Mamdani approach, very much well-known approach, okay, that follows linguistic fuzzy modeling. That means what? That means it will accept some linguistic terms. You know, I told you some examples at the beginning of the session, example of some linguistic terms, tall, long, short, like that. And it has the high interpretability. That means it is so simple. The steps of Mamdani approaches are so simple. Even a layman who don't have any concept regarding the fuzzy set, even they can understand the Mamdani approach. And obviously, it has some low accuracy. But since interpretability is very much high, that means it is very much popular among the researchers. On the other hand, this Takagi-Sugeno approach, it uses precise fuzzy modeling, very much high accuracy, and low interpretability. It is very much difficult, mostly mathematics, to understand this Takagi-Sugeno approach. Anyway, so we will go for this Mamdani approach only. So see, these are the rules, type of rules we use in the Mamdani approach. These are the two rules, R1, R2. If X is A1, Y is B1, then Z, that may be C1. This is a fuzzy set, This is these two input, these are the output, like that. Takagi-Sugeno model, see. So this here output is a function of both the inputs. It is something different, Takagi-Sugeno model. But in the Mamdani model, again, output simply will explore it in terms of this fuzzy set. But this is some function of these two inputs. Anyway, let us discuss, move towards this Mamdani approach. Fuzzy rule base. So rule base obviously we'll use to represent some knowledge. How to represent the knowledge? Once we have some knowledge, to represent the knowledge, we will use this Fuzzy rule base. And this is the general format of Fuzzy rule base, as you have seen. If this premise antecedent, then conclusion or consequent. As you have seen, if dirtiness is more and number of clothes are more, take wash time, more wash time, like that. Yes. Now let's see. One important thing here I will tell. So this is my rule 1, this is my rule 2. See, if X is A, then Y is B, where A and B are two fuzzy propositions. This is known to us, okay? See, now if I say in rule 2, if X is A naught, then Y is B naught. Now can we find B naught once we know this information? Yes. See what I mean to say here. Check the rule, check this thing very clearly. I am telling if X is A, then Y is B. This is known to us. Okay. And I am asking, you need to find out if X is A naught, then what will be the B naught associated with Y? That you need to find out. Now let me see some example. See, so again, so okay, that is some okay, let me check some example. Yes, see the example. See, so given a rule, if X is A, then Y is B. This is given, and this is A. A and B are fuzzy set only. So this is A, X and Y are variables, input variables. A and B are, these two are fuzzy sets. So this is the fuzzy sets, as you know. These are the elements. These are the membership grades. This is A. Similarly, this is fuzzy set B. These are the elements. These are the membership grades. Now see here. So that means if X is A, then Y is B. This is known to us. What we need to find? We need to infer B naught for another rule if X is A naught. See, where A naught is this. That means you know what is A naught. Then you need to infer what is B naught. How to do that? See how we are doing it. So this is, we can say, this is the fuzzy composition rule. So how we are doing it? Simply here I am writing, this is 5, this is 7, this is 9. Check it. So this 1, 5, 1, 5, minimum we will consider this membership grade, this membership grade. Here we are considering the minimum one. 0.2, 0.6, 0.2. This 0.2, 7, 0.5, 0.2. 0.2, 9, it is 0.4. So minimum, it is 0.2. So in this manner, we are formulating this matrix. Okay. So relation, better not to say matrix. This is a fuzzy relation. So here, whatever we are doing, we are using intersection. Intersection means you need to take the minimum of two membership grades, 1 and 5. We are doing the intersection between 1 and 5. 1 and 5 intersection, this intersection 1 and 5, that means what? 1 and 5 intersection. So here 1 means 0.2, 5 means 0.6. If you do the intersection 0.2 and 0.6, you need to consider the minimum one, that is 0.2. That's why I need to write here 0.2 like that. Anyway, so here these are the relations we are doing. Then this is given to us. How we compute this B naught? Let's see how we'll compute it. Again, check it very clearly. This is called max mean rule. Max mean, fuzzy composition. You see, fuzzy, once we are aggregating something, then we need this fuzzy composition rule. Fuzzy max mean is one of the very much popular and important rule for these fuzzy relations. Using this concept of fuzzy relation, we can take or we can generate or we can solve much more decision-making problems. These are some different rules: minimum, max mean, max product, min max, max max. Normally, we will use this max mean rule for that. Fuzzy composition rule. That means two different fuzzy sets are given. How to infer some separate decision based on these two fuzzy sets? Then you need to use this fuzzy max mean composition, like this problem. These informations are already given. So based on this information, you are generating a fuzzy relation. And using this information and this fuzzy relation, that means now what you will do? You will compose this information, this fuzzy set with this fuzzy relation to differ some decisions. See that? Or to infer some decisions. How I am doing, let us see. These fuzzy sets I need to compose with this relation. How to do? Minimax, max mean relationship. That means what? Firstly, I'll go for this row and this column. See, 5, 2. Max mean. What is 5, 2? 5, 2. Then 9, 5. 5, 2. This is 2. See, 9, 5. This is 0.5. 3, 6. This is 0.3. So all minimum I have taken. Next max of these three values, that is 0.5. Here it is 0.5. Are you getting it? Max mean relationship. Next, this row, this column, same thing. 5, 2, 0.2. 9, 0.5, 0.5. 3, 0.5, 0.3. Max is 0.5, this is 0.5. This is called max mean composition. See, so using this fuzzy set and this fuzzy relation, after applying the max mean relations, we are getting this decision. We are finding what is B naught. That will be the result for B naught. As I was telling, these fuzzy relations we can use in many decision making problems to solve. Okay, now we'll come to some another segment of our discussion, fuzzy systems, basically fuzzy logic system only. Now, at a glance, you can see. So this is the structure of this fuzzy logic based system. Grips input. This is a nutshell, very simplest manner I am trying to show it to you. Grips input, we need to fuzzify. We will get fuzzy input. We need to do some inferencing along with this fuzzy rule base. We will again, as a result, what you will get? You will get fuzzy output. Next, you should apply the defuzzification module, which will give you the Grips output. So this is a single glance. You can see what is the structure for this fuzzy logic based system. Yes. Now the question is that, so from the Grips input, how to generate the fuzzy output? Or from this fuzzy output, how to generate the Grips input? Many techniques are there. Today I will try to show you some of them. That triangular membership functions are there, trapezoidal membership functions are there, fuzzification. So we will show you something. Yes. So once we are converting a Grips value to a fuzzy value, normally we use this triangular membership function or this trapezoidal membership function. You know, triangle means it is a triangular shape, and this is the trapezoidal shape. You know, in triangular membership function, see that at one point membership grade will be 1. But in trapezoidal membership function, in a continuous range, the membership grade will be maximum. That is the difference between triangular membership function and this trapezoidal membership function. So this is the rule that here some power cut is there. Anyway, no issue. So just will connect the system. Just 1 minute. Must I'll switch off my video to otherwise it will again problematic. Just 1 minute. Let me see it is connected or not. Anyway, so I hope I am audible. So during my presentation, at any point of time, if you feel I am not audible, since it is a power cut once again here, so then please knock me. Otherwise, I will be continuing the presentation. I may not get to know I am audible or not. Once again, let me check the connections. It is ITW only. How it is connected. Anyway, I hope that I am audible as well as you can see my PPT. So we'll continue. So this is the, as I was telling, so this is the triangular membership function that you can compute in this manner. So this is X, okay, this is A, B. So now this is the way for that. Once is at X less than equal to A, that is 0 once this inside this X in between A and B, X in between B and C, then you can take these two rules, these two expressions. It will help you to generate this triangular membership value. And once again, C less than equal to X, obviously it will be 0. That means outside this. So similarly, it is the triangular trapezoidal membership function. Now this is the expression for that. So using this trapezoidal membership function, so from any Krebs value, see here, your X be the Krebs value. So from the Krebs value, you can generate the fuzzy membership grade. So these are the expression for this trapezoidal membership functions. So here better I will show you some example that how here I will show you some example that how you to use this triangular and trapezoidal membership function. Just check it very clearly. So here, so these numbers 25, 40, 48, 55, this is related with the age of some person. And these, the y-axis, so this is the membership grade. Okay. Here I am thinking that 25 to 55, so that may be the range for middle-aged person. And according to my perceptions, 40 means here exactly I can say that person is a middle-aged person. Okay, now tell me. So if I am in this region, suppose I am telling that is nearly it is 38. So once I am telling some age 38, that means it cuts the middle here and young here. That means on the age of 38, that person must be much more middle, because here is the middle. Membership grade of middle will be more than the membership grade for the young. I hope you are getting it. See, once I consider the age of a person is 38, then the membership grade associated with middle, that will be more rather than the membership grade associated with this young. Now see here. So this is an example for this triangular. This is the triangular membership function. Always it's in the shape of a triangle. So as I was telling, at one point, so membership grade will be maximum. And for the trapezoidal, so this is an example of trapezoidal, because in a continuous interval, continuous range, membership grade will be 1, and but for the trapezoidal and for the triangular, at only single point, the membership grade will be maximum or 1. Now see here, so here we are considering that one's age is 55 or more, then the person is old age person. That means if age is 60, then what is happening? Age is 60 means he touches here. That means the membership grade with old of that person is 1. That means that person is old only. But if I am thinking that person age is 48, it touches old here, it touches middle here. 48 means then the person is much more old rather than middle. Check, that's simple. That means 48, it has two membership grade. One is associated with old, old, it may touch here, membership grade, and middle, it may touch here. That means once we are considering the age 48, it has two membership grade. One associated with old, second one is associated with young. Sorry, with middle. And membership grade of middle is less, and membership grade for the old will be more. Now, here you can find this value of the membership grade using this triangular membership function, whatever I have shown you earlier. So this is the triangular membership function. So if you put this value here, we will get the exact membership grade. Yes, now we'll proceed towards a quick example. So just give me 1 to 2 minutes. I'll take some water. Then we'll proceed to another good example for that. Just once again, let me see. Okay, it is connected only. Just see the connections. Okay. Yes. So now we are discussing this system. Just see this system. So here we are using these two inputs, X and Y, and one output, that is Z. Now let us assume these are the membership functions. Okay, we have two membership functions. One is low T. This is the expression for that. One is the high T expression for that. Okay. Now let's see. Yeah, see. So once consider inputs, we have two inputs, X and Y. So let us assume that X equal to 3.2. So once X equal to 3.2, see here, then the membership grade corresponding to low will be 0.68. Touches here. Okay. And membership grade corresponding to high will be 0.32. See here, this is the high membership grades or triangle related with high. So that means it touches here, that it is 0.32. All we are getting it from this, I think, from this triangular membership function. Okay. Now, these two are values related with 6.1. Once y equal to 6.1, see, what is the membership grade with this low membership function? What is the membership grade with this high membership function? Here you can directly find, since it is the expressions are given. See here, low T. See, low T means what? 1 minus T by 10. See here, low X. Low X means what will be there? Then 1 minus T by 10. See, low, that means 1 minus 0.32, it will be 0.68. See, high X, high T by 10. What is T? T means here X. So once it is 3.2, 3.2 by 10. 3.2 by 10, that means it is 0.32, like that. Similarly, we are finding the membership grades for low and high corresponding to our input variable Y. Okay. Next, what to do? See that. So from this, that means from the input variables, now using the fuzzification module, we have converted the input variable into corresponding fuzzy membership grades. Let's see. Our fuzzification is over. Okay. Let's see. And these are the rule base. Suppose it is given. Rule 1. If X is low and Y is low, then Z is high. Rule 2. If X is low, Y is high, Z is low. Similarly, this is my rule 3. This is my rule 4. Suppose these rules are given for that. Try to get it very clearly. So in rule 1, it is high, Once both is low, x and y is low, rule 4. Again, z is high when both x and y are high. Otherwise, it is low only. This is my rule base, it is given. Okay, next. See. Now I need to do some inferences based on my rules. See how I am doing the inferencing. This is the task of the inference engine. See here, rule 1, how I am doing. See, wait, let us check it very clearly. Rule 1, x is low, okay, y is low. Check. Rule 1, check. X is low x, okay, 0.68, low y, 0.39. You may ask me, sir, where you are getting these values, 0.68, 0.39. See here, I am getting these values from my previous slides. Low, 0.68, low x or low y, 0.39. This is not random. We have some specific this membership function. Based on the membership functions, we are getting those values. Okay, so both 0 values. Then what you need to do? If both are low, then what your rule is telling? Then z is high. See, z, you need to find the high z, and here we will use the minimum of these two membership grade, 0.68, 0.39. That will give us 0.39. You know what is actually the significance of this value? This value identifies the strength of the rule. 0.39 means it is the strength of rule 1. Similarly, you can find out in rule 2. What it was in rule 2? If x is low and y is high, okay? X is low, y is high. Now, see here, low x means 0.68, high y means 0.61. We are getting it from our previous slides, these values, okay? Then, what will be your z? Your z is low. See here, how I am finding the value of z? Low z. See, here I am considering z will be low. Here I am considering the minimum of these two membership grades, 0.68, 0.61. I am getting 0.61. Again, this identifies the strength of this rule 2. Similarly, I am finding this rule 3 and rule 4. See, inferencing. So here based on the values I am receiving from my classification module, my inference engine is working. Here, whatever I have taken, here I have taken 4 rules and I have evaluated or I have fired all these 4 rules for the simplicity. But normally in the rule base, more number of rules will be there, and once you are firing, maybe a subset of rules only will be fired. I hope that up to this point you are getting. Now these are the strength of these rules. So our inference engine task is over. Next, what to do? See. So from here, what you are getting? You are getting 2 high values, this high z, 2 high values for z, as well as you are getting 2 low values for z. Then what to do? That means you need to compose. You need to compose this high z and 2 low z values. How to compose? See. Actually, this is the max-min compositions. So initially we are using the minimum, then we are maximizing the values. This is called as max-min compositional rules. See. Low z. Low means where z was low. Check very clearly. This rule 2 and this rule 3. Z was low. Okay. So that means low z, max of rule 2, rule 3. These two values, these are the strength of rule 2. This is the strength of rule 3. Maximum means this one. Similarly, high z, that means rule 1, rule 4, max of 39, 32. It will be 0.39. Are you getting it? How I'm composing? As I was told previously, max-min composition. Initially, we are doing the minimization. Then we are trying to find the maximization. Now, whatever you are getting, we are getting one value for low z, second value for the high z. See, we'll plot it. So this is our low This was the low triangular membership function. Here the plotting will be there. Okay, this is the value for 0.61. So correspondingly, position will be this. And for high, this is the membership grade, and so it will cut this. It will cut this high here only. So this will be the thing. Now let us see. Now let us plot it. Let us plot this. Yeah, what will happen? Let us see what I am doing. So since this 0.61, this is the membership grade associated with this low. That means this part is not required. We may discard this part. Simply I am discarding this part. Are you getting it? Take it very clearly. I am discarding this part. Okay. And remaining things. So this 0.39 associated with this high here only. So that means I will take from this side only, but this part I need to take. This part from this and this I need to consider. Take it here. Yes. So simply I have taken a union. I have taken a union of both these two things. Okay, next what I will do. So next we need to find out that, so we have now the membership grades. Our inference engine task is over. Next we need to do the defagification. Defagification means what? From this Scripps output you need to convert, from this fuzzy output you need to convert into some Scripps output. How to convert it? So that is the task of the defagification module. So defagification module, a number of defagification techniques are there. So that is center of gravity, max sum, center of sum, many things are there. So today we'll try to restrict ourselves into some of the techniques. Center of gravity. See, center of gravity. So how it will find out? Check it very clearly what I am trying to do. So this is pictorially center of gravity of this entire this region. So maybe this region. So this is conceptually. I will show you numerically how to find it out. So this position. That means, so corresponding Scripps output will be this one. What is the value of this position? That will be the Scripps output for the entire process. So this is the concept we are getting conceptually or simply graphically. Now, how to get it numerically? So this is the expression for that. Here we will not use this continuous region. So I will try to make it much more simpler using some Scripps values, discrete values. Yes. So this is the centroid. I will show you. This is the formula or expression for the centroid method. So xi mu xi. Okay, summation of all these mu xi. See. This is the expression for that xi, summation of xi, mu xi, and this is the summation of all this membership grade. Let us take some example. Yes, let us see this. Here it is given very clearly. See. So at this point 0, this is a discrete one. Earlier that was continuous one. So in this 0, 0. See, take it very carefully. 0 membership grade is 0.1. 10 membership grade is 0.1. 20 membership grade is 0.1. That's why I have written in this manner. Okay. Next 30, 40, 50, 60 membership grade is 0.2. That's why I have written it in this manner. 70, 80, 90, 100, 70, 80, 90, 100 membership grade is this one. Okay, 0.5. So writing in this form. And what will be here? So summation of all these membership grades. 0.1, how much time I have used? 1, 2, 3. That's why 3, 0.1. 0.2, how much times I have used? 1, 2, 3, 4. That's why 1, 2, 3, 4 like that. So here I am finding 67.4 this. So this will be my Scripps output. So this is the way we can convert that our membership grade into some Scripps values. Now quickly within the last 15 minutes, so I think most of the concept I have covered with this using this fuzzy logic. In the last 15 minutes, quickly I will tell you an application of this Mamdani approach, and that is the concept of mobile robot. Now here the consider the control of navigation of the mobile remote in the presence of a number of moving objects. Here we will consider that a robot is moving as well as some objects are also moving. So for the sake of simplicity, here we will consider that only 4 moving objects are there, and each of the moving objects are of equal size and moving with the same speed. Getting? So that we will consider here. But in real life, the situation may not be the same. But for the sake of simplicity, we will work in that manner. See, this is the graphical representation. So this is our robot. Okay. So these are all the objects. They have same size, same speed, all they are moving. It is moving in this side, like that. It is moving in this side, it is moving in this side. So what is our objective? So that our moving robot should not make any collision with any other moving objects. So how to avoid the collision? So that we will try to determine using our fuzzy logic controller based system. Okay, so here 2 concepts are there. 2 input parameters. One is the D. D means distance of the robot from an object, and theta means the angle of motion of an object with respect to robot C. D means what? Distance of the object from the robot. Theta means what? This is the angle. This is the angle of C. So this is, yeah. So this is the angle of motion of an object with respect to the robot. Angle of motion of the object with respect to the object. This is the angle of motion of the object with respect to that robot. So this is the theta. 2 parameters. One is the distance of the object from the robot. Second is the angle of motion. So 2 parameters here we will consider. Okay. Now here also we will see that once we will input these 2 parameters, then based to these parameters, the robot will deviate its path or not. See, our objective is to find out the deviation. Deviation means how much angle the object, the robot should deviate so that there will be no collision. Okay. Yes. With respect to most critical object, it will output deviation. Object should deviate from the robot should deviate from its path so that it can avoid some collision with that particular objects. Okay. Again, for the sake of simplicity, we will assume a range of values. Distance, it will be from 0.1 to 2.2. Okay. Luckily, again, power came. Okay. So it is in meter, and theta, we will consider the theta value from -90 to +90 in this range. Okay. So this is our assumption for that. Now let us see. See. So as I was telling, that entire concept now I'm going to implement using this fuzzy logic based controller. Yes. So here we will consider some linguistic states. As you know, the Mamdani approach always works with these linguistic terms, linguistic fuzzy variables. Here, for that, how to represent the distance, we will use these linguistic terms. Vn, very near, Nr, near, Vf, very far, Fr, far, like that. Distance. To represent the distance, we will use these 4 linguistic terms. And to represent the angle, both for angular direction and for the deviation of the robot, angular direction of the objects as well as deviation of the robots, we will represent using these 5 linguistic terms. LT stands for left, AL ahead left, AA ahead, similarly these 2, ahead right, right. See the fact. So these linguistic terms I am using to represent the distance as well as the angle, both for the angular direction of the objects as well as the deviation of the robots. Now, see, this is very much important one. See here. Let us see. So once the distance of the robot from the object, from a critical object is 1.04. See here. Here I am finding this is 1.04. Okay. Object, distance of the object from this critical object from this robot. This is 1.04. Once the distance is 1.04, that means it touches this triangular membership function here only. That means what will be the value for that? It will get a value for this near. So near linguistic terms, NR, NR stands for near. So near linguistic terms, that means, so it will get some value here, and also it touches the axis far here, near and far. So that means, so near and far for these two linguistic variables, we will get some fuzzy values. Getting how to convert the linguistic variables into fuzzy values. So we are getting the fuzzy values corresponding the linguistic variables. Simply, if we consider that angle, so that, as I told earlier, that angle, yes, for both for the angular direction and for the deviation. So if we consider the angle, suppose angle be 30. If the angle be 30, then what will happen? Let us see. Angle, which angle I am considering? This angle I am considering, this angle. So here the angle is, suppose it is 30. Okay. So if it is 30, that means, so here it may touch both this ahead and ahead right, ahead and ahead right in this position. That means the fuzzy membership grade with these linguistic terms ahead and ahead right will be this one. Okay. So that means using these triangular membership functions, here I am trying to finding out the membership grade associated with these linguistic terms based on the inputs. Okay. And deviation, so this is our objective. We'll try to find the deviation of the robot. Okay. Let us proceed. So these are the fuzzy rule base. See here. Fuzzy rule base. So here, so this is represented in terms of a matrix. We'll say in terms of some relational matrix. Okay. So how it is, see that? So if it is very near, and it is left, see that, as I was telling. So if the object is very near, and left, and angle is left, so that means, so ahead. So that means the deviation of the robot should be ahead. Let us check it. So these are the rules I have formulated. Very near, left, angular direction, deviation of the object should be ahead. If it is very near, ahead left, so that means the deviation of the robot should be ahead right. If it is very near, and this is ahead, the angle is ahead, angle of the object with the robot is ahead, that means the deviation of the robot should be this ahead left. So these are the rules I have formulated. These are the 5 linguistic terms associated with the distance. These are the 5 linguistic terms associated with the angle. So how much rules are there? We will find out total 20 rules are there based on our inputs. Okay. Now let's see. As I was telling, so these are the rules. 20 rules are there. Rule 1, distance is very near, angle is left, then deviation should be this. Rule number 20, distance is very far, angle is right, deviation is ahead. Getting? So these two are the inputs and this is the deviation with the output. Okay. Now let us come to the part of fuzzification. Already I told it, fuzzification, that here we are considering the object O3 be the critical object. So we are finding that we are assuming that there is a chance a robot may collide with O3. Okay, others we are not considering it. Next, so here we are considering the distance of that particular object 3 with that robot is 1.04 meter, and angle of that object with the robot, so this is 1.04, and here we are considering this is 30. So these two things we are considering. Now we have to decide the deviation delta of this robot as an output. So what will be the deviation of the output? Here we are assuming that robot is moving, robot is supposed to move in that direction. This is the direction that robot should move. But if in that direction robot is moving, obviously there is a chance of collision. So we should find out how much will be the deviation of the robot to avoid any collision. See, so already I told that using this concept of these membership functions, so we are getting the membership grade. So we are getting the membership grade corresponding to that linguistic terms. Okay, as I was telling that the 1.04 may be called as near or far. 1.04 check. So this is the near triangular membership function and this is the far membership function. So these two membership functions it is touching here. And here angle theta 30 can be declared as either ahead or ahead right. Check it here. So if I declare this is 30, so it may be associated with this ahead or this ahead right. That means, see here. So we will work only on this near and far. So these two linguistic terms as well as ahead and these linguistic terms. I think so. This along with this, yeah, this is ahead right. So these four linguistic terms only will be there once we will proceed further. Now see very carefully. So this is the fuzzification of our input. So I will not go into detail. So due to this x, once x is equal to 1.04 meter, so then what will be the membership grades associated with the near linguistic terms associated with far. So this will be the membership grade of x associated with near. This will be the membership grade of x associated with far. These two membership grades we are computing based on the values of x. And these two membership grades we are computing based on the input values of y. As I was telling, so this is this starting here. That means we need to compute this ahead and ahead right. Okay. Next, what we are doing? Now this is here. Actually, some noises are coming from the participant side. So I will request the participants to please mute your microphone. Otherwise, it is I am finding it difficult to share my thoughts. Please mute your microphone. Yes. Yes. So now this is fuzzification of input. See that. So here actually based on the rule of similarity, principle of similarity, here I have computed the values. What about the membership values I was showing you that how these membership values is computed, how this is computed. You can compute using the triangular membership functions. Here again I have given you another rule, that is the principle of similarity. Here also we can compute in this manner. Ultimately, so we have got that particular 4 fuzzy values for those linguistic terms. Then what we will do? So that means fuzzification module is over. So we will go for this. We have this fuzzy rule base already we have built up. Now we have also developed the fuzzy values corresponding to Krebs input. Next, our task will be assigned to fuzzy inference engine. Let's see. As I was telling, this is the fuzzy rule base. Now, if you look closely, only these two linguistic terms we need: near, far, and this ahead and ahead right. Check it very clearly. Here, near, far, ahead, ahead right. Other terms, linguistic terms are not required. That means, so only if we do, that means only these things. I think yes, this and here and here. That means only these 4 rules we need to evaluate our problem. See here. We may have a number of rules in our rule base, but here inference engine, now we will explore or evaluate only these 4 rules, okay, to solve our robots related problem. Check it very clearly. Yes, so as I was telling. So only these rules will focus. Remaining rules we are not required. Okay. So as you know, what is now rule 1? If distance is near, angle is ahead, then deviation should be right. So this is we are getting from the rule base. Okay, and these two inputs are given. Next, as per our concepts, what you need to do? You need to find that what is the strength of each and every rule. Next, we will proceed. See here. Similarly, the earlier examples, what we did? This is the strength of each and every rules. How we are finding? Check it. Minimum of membership inner, membership ahead. See here. Membership associated with near, membership associated with ahead. This is X, this is Y. So if you look, that means, so this your mu inner, that we got this value. Mu ahead, we got this value. So these all we computed in the earlier step. So that means we will calculate a minimum of these two. So that will give us 0.33. So similarly, you can find in this manner the strength of the other rows. Similar manner, you need to find out the minimum of those two membership grades where you have calculated in your earlier step. Okay, now here one important task is there, that in practice all rules which are above certain threshold value that will will use for the computation purpose. Now we will find out which is the threshold value. Here this is the, I think, task of the fuzzy programmer, that we need to find out which is the threshold value for that. Here for our simplicity assumption, we will consider threshold value be this. That means, so these two rules now we will consider for our computation. So this R2 and R4, since this is above this threshold value 0.34. Okay. Next, what you will do? So next, so we need to that you have seen. So that means we are getting to membership grade. So we need to compose, and ultimately after composing, so we should get some creeps output. So how to do it? How to get that? Okay. So anyway, so this is the way. So here I will show you. So what quickly I will show you what I am doing here. See, for the mobile robot. So this is for robot 1. This is for robot 2. I have plotted that those two rules, whatever I consider for computation, plotted in this graph. Okay. So this is for R1. See that this is for NR. This is for near, and I think this will be for the far, FR, and this is for ahead. Okay, so now if you just pictorially see here, so here we are getting here in this month, so this is our area we are getting. So similarly, you are getting here in this area. Now, if you I think take the union of all those areas, then what you will get as a result. This is the defugification process. Now we are proceeding. See here. See. So see here, so what I am getting, so all four things are there. See that this is right, ahead, okay, this is ahead, right, this is ahead. So all we are combining. That means we are making this, I think, yeah, all we are combining, that means union operations on all these areas here we are considering. Now, as you have seen earlier, I have shown you one defugification module. So based on that, here we will defugify. We'll take the aggregation of all these results. So here I'll not go in detail. Now here that will be our result after defugification, whatever I have shown you earlier, that center of gravity, COG. So here this will be our result for that. Actually, I am doing exactly in similar manner, whatever I have shown you earlier. So see that. So from the fuzzy inference engine, we computed those rules which are of much more strength based on some threshold value. Then we initiated our defugification process. And based on the defugification process, we are getting some creeps output, 19.59. Here we can say our conclusion is that the robot should move or should deviate by 19.58 this degree towards the right. See here, towards the right with respect to the line joining to the move of the direction to avoid collision with the obstacle or with the object 3. Why it is I am telling right? Because this is positive. So that's why I am telling this is right. If it is negative, that means that would have been left. So see here. So how important it was that to find out that what will be the deviation for the robot based on the inputs when some objects are moving. Okay, so that using the fuzzy logic controller, we computed what should be the required deviation of the robot so that we should avoid some kind of collisions and our robot navigation should be smooth enough. So this is a very, I think, important application of robot navigation using this fuzzy logic controller. And actually in real life, all objects are moving and in different speed. Size of objects are very much different. So actually once this is the fact, then the things or the logics will be much more complicated. But again, that we can solve using this fuzzy logic controller based problem. Okay, so now thanks to everyone, particularly thanks to the participants for listening me in this one, I think, last 2 hours. So now I would like to take some questions from the participants. So if there are any questions, participants, please feel free to raise your questions. Also, you can type in chat box. So feel free if you have any kind of questions, I'll be ready to answer for that. Also, participants, please take a note of my email ID and contact number. So again, in future, if you have any doubt, any queries, please feel free to drop me an email in this email ID. And this is my also WhatsApp number. You can contact me through WhatsApp also. So I'll be ready to do some collaborative work with my participants.
Thank you, sir.
So please raise your questions, participants. Please, if you have, let me check the chat box. Yes, I think Dr. Sanjay Kumar Panda sir also has typed my email ID and contact number. So participants, please feel free to communicate with this contact number and email ID. Now, if anyone have some quick questions, as I was telling, I am ready to take.
We'll close the session here, sir.
Yeah.
I think there is no
Yes,
question.
yes. So once again, so I would like to express my sincere thanks to the coordinators of this FDP. So particularly Dr. Sanjay Kumar Panda sir for inviting me to deliver my thoughts here. So once again, thanks to the participants for their patience. So thank you.
Thank you, sir. Thank you very much. So we'll start the next session. Madam has already joined. We'll start the session at 5:10. Manju madam, shall we start?
Yes, we can start.
I welcome all of you to the second session of day 7. So in this session, we have Dr. Manjuwala Vaisi madam. Madam will discuss about the class imbalance problem. So I request Manju madam to please start the session.
Yeah, good afternoon all. Am I audible?
Yes, madam, audible.
So in this session, I am going to talk about the concept of outlier, how to detect the outlier and how to prevent the outlier, along with the class imbalance issue in machine learning problems, and how to handle this class imbalance issue so that the performance of the machine learning models will increase. So this is the outline of the talk. So we'll see what are the types of outlier, how to detect the outlier, how to prevent the outlier. Then we'll see some of the class imbalance learning approaches to balance the data set. So we'll see some oversampling approach, we'll see some undersampling approach. You have to make link and near miss algorithm. These are the two undersampling approach. And along with that, your synthetic minority oversampling technique and adaptive synthetic sampling approach. These are the two oversampling approach. At the end, I will show you a case study, and we'll see how this imbalanced learning approach can increase the performance of the machine learning models. And if time permits, I will show you some demo in Python, along with some diversity-based oversampling approach also we'll discuss. So coming to the outlier, right, we have studied the statistics. So in statistics, outlier, this is an observation or this is a data point in a data set that is far away from the other observation, or that we can call that is the distance from other observations. So generally the outlier or a data point, it deviates significantly from rest of the data points in the data set. Right? So how this outlier are coming into the data set? Mainly they are caused by measurement or execution error. So we have to find out these outliers in the data set, and for that we have to analyze our data, right? So analysis of outlier data, we can call this is the outlier analysis or outlier mining. So for outlier mining, we have to follow different procedures to find that outlier, and we'll see how to prevent this outlier in the data set. So this is a simple definition. The outlier is something which is an odd one out, or the one that is different from the crowd, right? And that behavior is different from the rest of the points in the data set. Right? So concluding that the outlier, this is a data point that is far away from the other points in the data set. Right? So how these outliers are introduced into the data set? So generally outliers are introduced into the data set of the population while we are gathering the data or we are collecting the data. Right? So data can be collected in many ways, right? We can conduct interview, we can perform some questionnaires, we can do some survey, right? We can do some observations, right, from an experiment. We can find out some documental records. From there, we can collect the data, right? Or we can do some group discussion, oral history, right? And in this technology era, now different sensors we are using for generating data for us, right? So while we are collecting this data, at that time, these outliers may be introduced into the data set. So another another possible cause of outlier that could be your incorrect entry in the data, right? Suppose we are maintaining the record for the data set, right? So whenever we are entering, somebody is entering the data, due to incorrect entry in the data set also, outliers may be introduced. Or it may be misreporting of the data or misreporting of the observations and sampling error, right, while doing the experiment. Suppose we don't have the real data or the actual data, so we are doing sampling process to generate the data. So during that experimental way also, some outliers may be introduced into the data set. So generally these outliers, we can tell that these are the mistake during the data collection or what it indicates. So outliers, when we say that outliers are present in the data set, that is just indication of variance in your data set. So the data points, whatever n number of data points are there in the data set, so the variance will be very high among the data points. So coming to the types of outlier, so generally there are three types of outlier: point or global outlier. Second one is the contextual or the conditional outlier, the collective outlier. Right. So from the name itself, you can understand what is this point outlier, conditional or the contextual outlier, or the collective outlier. So point means, right, we are having the data set. So that one data point is considered as a outlier, that is a point or the global outlier, if its value is far outside the entirety of the data set in which it is found. Right? So majority of observations will be there. So one single data point, right, that will be far away or whose behavior is different from the remaining data points. So that is called a point or the global outlier. Suppose we are having a student record, right, where we are maintaining the age of the students, right? Suppose the students belong to the BTech, right? BTech in the first year to final year, right? Suppose we are getting a record of age, right? Student age is 100. That means you can call this is an outlier, and this may be right, could be generated due to various reasons, whatever we have discussed in the previous slide. Coming to the contextual or conditional outlier, so with respect to some context or with respect to some condition, some observations are called as or the data point is called as an outlier, but it is not called an outlier with respect to some other context, right? So observations considered anomalous with respect to a given specific context. A data point, this is considered a contextual outlier if its value significantly deviates from the rest of the data in the same context. So the same value may not be considered as an outlier with respect to another context. Suppose if you maintain the world economy, right? So due to COVID-19 in maybe 2020 and 2021, world economy falls drastically, right? If you observe such records, right? So this is the, you can call this is the contextual outlier, because with respect to COVID-19 only, this changes occurs. Next, the third type of outlier, this is the collective outlier. So collective outlier means a collection of observations or a collection of data points. Their behavior is different with respect to other points in the data set. So a collection of observations, anomalous, but appear close to one another because they all have a similar anomalous value. Right? So subset of data points within a given data set is considered anomalous if those values as a collection deviate significantly for the entire data set. Right? But if you consider the individual data points, they may not considered as a outlier. Right? So with respect to collective approach, we can call those points that deviate significantly from the rest of the data. So basically, this collective outliers present in the time series data, where a group of data points, right, or a collection of data points, their behavior deviates significantly from the rest of the data. So what is the importance of identifying these outliers, right? So as we are, right, machine learning algorithms we are using, right, for doing some solving some prediction problem or some regression problem. So we know that the machine learning algorithms, right, whatever they are designed, they are very sensitive to the range and distribution of attribute values. So whatever training data we are using, right, in the training data maybe more than one attributes are there. So the algorithm's performance depends upon this range and the distribution of the attribute values. So if the outliers are present in the data sets, right, so they can spoil and mislead the training process, so which will lead to longer training time, right? Raise accurate model. I mean, the accuracy of the model is not good, and ultimately you will get poorer result. Right? So due to this, we have to identify if any outlier is present in the data set. Right? Suppose you are having a data set to solve a particular prediction problem or regression problem. So first we have to, before applying the machine learning algorithm, we have to do the pre-processing of the data, right? So this outlier, identifying the outlier and right, how to overcome these outliers, these are coming under the pre-processing step in the machine learning algorithms, right? So how to detect these outliers? If any outlier is present in the data set, And so what are the techniques we have to follow to detect the outlier? So there are basically two simple techniques to detect the outlier. First one is the visualization technique. Second one is the mathematical function. So under visualization technique, we can do the box plot, histogram, or the scatter plot. By using these three plots, we can identify or we can detect the outliers present in the data. And the mathematical function, we can apply the z-score, right? And we can use the interquartile range IQR value we can apply from a given data set. First quartile, third quartile, and the second quartile we can determine. And by using those three quartiles, we can find out the interquartile range. Then we can identify which points are called the outliers in the data set. So the visualization technique, this box plot says you know how to draw the box plot from a n number of data points are there, and this is suppose the box plot, right? So this is the mean of the data points, right? So if you see these 2 points, they are deviating significantly from the mean of all the data points, right? So these 2 points we can call this is the outlier in the data set. So you can identify, you can detect the outliers in the data set. Second one is if you draw the histogram, right? So histogram, you know, the x-axis you can represent, right? Suppose this is the age of the students and the x-axis, and in the y-axis this is the frequency, right? So within this range, how many students are there? That's frequency. If you plot this histogram, right? If you see these points, right? The frequency is very less. Those we can call this are the outliers in the data set. The third one is the scatter plot, right? This with the x-axis, this is the x attribute. This is the y-axis is the y attribute. So if you draw the scatter plot, right? If you see these points, right? This point, this point, this point, right? So this point, these are right, or these are far away from the remaining points. So we can consider, right? These points are the outliers present in the data set. So these are the three visualization technique: box plot, your histogram, and the scatter plot, by which you can detect the outliers in the dataset. And coming to the mathematical function, one is your z-score. Now, if you know the normal distribution, right, it depends upon the normal distribution. The z-score, if you know, this is one of the important concept in the statistics. So it helps to understand if a value, data value, is greater or smaller than mean, and how far away it is from the mean, right? So it is whether 1 mean, 2 mean, or 3 mean far away, we have to calculate, right? So generally it tells how many standard deviations away a data point is from the mean. So this is a simple mathematical formula you can use. Z-score equals to x minus mu by sigma, right? So if this z-score value of a data point, this is more than 3 mu we are using, right? It indicates that the data point is quite different from the other data points, and this can be considered as an outlier in the data set. Next one, this is the next mathematical function, that is the IQR score, interquartile range score. So if you are having a data set of n points, you can divide the data points into 3 quartiles: quartile Q1, quartile Q2, and quartile Q3. So this is the Q3 range, right? The upper limit of Q3. This is the upper limit of Q1. So you find out the IQR, interquartile range, that will be your Q3 minus Q1, right? Then if you find, right, the upper beyond this point, Q3 plus 1.5 into IQR, if any data point is present, that point can be considered as the outlier. So up to this, your points are not outlier. Similarly, beyond this Q1, right, that means the beyond to the left side of Q1, that means in the lower region of Q1, if you consider the range as Q1 minus 1.5 into IQR, interquartile range, so whatever points are coming beyond this region, they are called the outliers. And this quartile Q1, Q3, this quartile range, you can calculate by using the median values. Again, some simple formulas are there. If the data set contains even number of points, you have to use some formula, and if the data set contains odd number of points, you have to use some other formula, depending upon the median value. Right? So if you apply this mathematical function, you can able to detect the outliers present in your data set. So what are the, once you have detected the outliers in your data set, right? So how to prevent these outliers from your data set, right? So generally the prevention of the outlier in the data set depends upon the domain knowledge and the experience with the outliers. So complete domain knowledge for which you have collected the data that is required, right? If you are having the domain knowledge and the experience with the outliers, so you can prevent those outliers in the data set, right? Second one is you have to drop the outlier record. This is very easy, right? Suppose some outlier data is there, that means the odd one you are getting. So simply we have to drop that record, right? We are removing that record. So, but generally it will not work in every scenario, right? So sometimes it's best to completely remove those records from your data set to stop that skewing your analysis, right? Because due to this outlier, variance in the data set is increasing. So that's the skewness is coming, right? So sometimes it is easy to drop that outlier record also, or the outlier data point. Third one is you can cap your outlier data. So capping means what? Suppose, right, some data points, right, they are having same behavior with respect to some threshold value or the threshold level, right? So you can keep or you can cap those threshold value as the value of those outliers data, right? So this is another way to handle the true outliers, is to cap the outlier data in the data points in the data set, right? So suppose we are using the income attribute, right? So we will find that, right, some cases people above a certain income level behave in the same way, right, as those with a lower income, right? Suppose those who are getting income is monthly 50,000, 60,000, 70, 80. Above 50,000, their behavior is different, and below 50,000, their behavior is different, right? So similar type of behavior we are getting if the income is above 50,000. So for the 60,000, 70,000, 80, 90, whatever the upper values we are getting, we can cap those values at 50,000, right? So that is the, you have to cap your outliers data. Again, that depends upon the domain knowledge, right? So what is the behavior, right, of the data points with respect to a particular value. Using that domain knowledge, you can cap the outliers data. Fourth one is you can assign a new value, right? So if an outlier seems to be due to a mistake in your data, right? So what you have to do, you have to try imputing a new value. So imputing means you have to assign a new value, but randomly you cannot assign a new value. So some statistical inference you have to follow, and you have to assign some new value to that outlier. So that way also you can prevent the outliers from your data set. So generally the common imputation methods include, you can use the mean of a variable, or utilizing a regression model to predict the missing value also, right? You can consider that as a missing value, and you can use the regression model to find out that value of that outlier, right? That means the old value you are replacing with a new value. You are assigning with a new value, but with some rules you are following, and you can assigning those values. And at the end, that is another method, you can try for a transformation, right? So this is a different approach to detect the true outliers in the data set. So you can use that your different normalization you can do, right? The transformation you can do, mean max is there, so that it can transform all the values in the range 0 to 1, right? So in that way you can apply some mathematical functions to transform the data, original data, to some other form, but with respect to some range, right? So these are the some basic, right, your prevention methods. If you, in your data set, right, if you are having, you are able to detect the outliers by using any one of the visualization technique or any mathematical functions, then you can apply any of these prevention method to handle the outlier in your data set. So this is the pre-processing you have to do before applying the machine learning models, right? So the next one is, this is the class imbalance issue. This is also one pre-processing step you have to do whenever you are solving the problem, any regression or the prediction problem by using machine learning models, right? So what is this class imbalance issue? Generally this happens with a classification problem, right? So when observation in one class, this is higher than the observation in other class, then there exists a class imbalance issue. So what happens? Suppose we are having a software, right? In the software, suppose there are 100 fault prone modules are there, and suppose 9,000 non fault prone modules are there. Okay, so if you want to predict the class, right, for the modules of the software, so what happens in this case? So majority of the classes are your non fault prone modules, and few classes are fault prone modules, that is called your minority classes, right? So whenever you will use this data as training data into any machine learning algorithm, what will happen? This will hamper the model accuracy, right? Because majority of the models are 9,000. So maybe the model is biased towards the non-fault prone models, right? So whenever you will test your model, right? What will happen? Many cases, most of the models, they are predicted as non-fault prone, right? It is not due to that we have trained our model properly, right? It is not that, because it is biased towards the non-fault prone models. Right? So the problem with class imbalance issue is that most machine learning algorithms work best when the number of samples in each class are about equal, right? Because there is no biasness here. Equal number of samples are coming for each category or each class, right? Because most of the algorithms, they are designed to maximize the accuracy, and they have reduced the errors in the training process. However, if the data set is imbalanced, in that scenario, what will happen? You will get a pretty high accuracy just by predicting the majority classes, right? But you will fail to capture the minority classes, because this is biased towards the majority class. More number of samples are there. So what will happen? What will happen with this class imbalance issue? So accuracy will mislead here, right? Because for all non-fault modules, you will get 100% accuracy, because this is biased towards the non-fault modules. Majority of modules are non-fault, right? But whenever you will test for the faulty modules, fault-prone modules, you may get 0% accuracy. For the overall accuracy, you will get good accuracy, right? Why you are getting the overall accuracy is good, or it is very high? Because most of the modules are non-fault prone. Not due to that your model is very good, you have trained the model very well, and your accuracy is good. No, because your data is biased towards the non-fault prone models. That's why you are getting good accuracy with respect to this majority classes, right? So in that scenario, your accuracy will mislead, right? So for that purpose, we have to tackle this class imbalance issue very carefully before applying any machine learning algorithm, right? So, how to balance this data, right? Suppose we are having this class imbalance issue in our data set. So, very simple technique is your sampling or the resampling technique, right? It's a very widely adopted technique to deal with this highly imbalanced data set, right? So, generally, there are two types of sampling. You can go for the undersampling, you can go for the oversampling. So, undersampling means you have to remove the samples from the majority class. Okay, and from the minority oversampling means this is just the reverse of the undersampling. You have to add more examples from the minority class, so that the total samples, right, samples from the majority class and the minority class will be balanced. So if you see this diagram, this orange color, this represents the minority class. This blue color represents the majority class. If you apply the undersampling approach, so the majority samples you are going to remove here. So now the data set is balanced. So some of the samples from the majority class you are removing here. And just the reverse in the oversampling, what will happen? This is the majority class, blue color, and the orange color is the minority class. So you have to, you have to add more samples for the minority samples. Now, thus both the samples with respect to the majority class and the minority class are equal. So in this way, you can apply this oversampling and undersampling technique to balance your data set, right? So whenever we are doing this simple oversampling or undersampling, so what are the problems, right? What are the problems that may arise, or in which scenario we can go for this oversampling and the undersampling? So the simplest implementation of oversampling is what we are doing. Simply we are duplicating the random records from the minority class. Right? This is we are adding the samples from to the minority class. So randomly we are duplicating the records from the minority class. So it may cause your overfitting, right? So in the undersampling, what will happen? Similarly, you are removing random samples or the random records from the majority class, which may cause your loss of information. Right. So these are the things you have to take care whenever you are applying any imbalance learning approaches to balance your data set. Right? So in which scenario you can go for this random undersampling, right? So as we have seen, the undersampling, this can be defined as removing some observations of the majority class, right? What we have to do, we can do, right? We can remove the observations from the majority class until your majority and minority class is balanced out. Right? So this undersampling, this can be a good choice. So when we can apply this undersampling, when we have a ton of data, we have sufficient data. Think suppose we have millions of samples are there, right? In that scenario, we can remove some of the observations. So in that scenario, we can go for the undersampling. But a drawback, as we have discussed in the last slide also, right? So some of the observations we are removing, right? As we are removing some of the observations, some valuable information also we are removing from the data set, right? So that you have to take care. And in the random oversampling, this can be, right, defined as the adding more copies to the minority class. So randomly again we are adding more number of minority samples into the minority class. So when we can apply this oversampling, when we do not have a ton of data to work with, right? When we have less amount of data and we can randomly add same copies from the minority class. Right? And as we have seen in the previous slide also I have discussed, due to this random oversampling, it can cause your overfitting and the poor generalization to your test data. Right? So in which scenario, right? So whether you have to go for the oversampling or whether you have to go for the undersampling. So those two things, the available information, it should not miss. And what is that? It should not provide your generalization problem or the overfitting. Okay. So coming to the undersampling, so one is your Tomek link. You can use the Tomek link technique to balance your data set. This is your undersampling approach. That means we have to remove some of the majority classes. Right? So how to do this one? Tomek links, first you have to find out the Tomek link, and from the Tomek link you have to remove the majority classes. So what is this Tomek link? Tomek links are pairs of very close instances belonging to the opposite classes. Right? So what you have to do, you have to remove one side, you have identified the Tomek link, right? So you have to remove the instances of the majority class for each pair. That increases the space between the two classes. Right? So Tomek link exists if the two samples are the nearest neighbors of each other. So if the two samples they are nearest to each other, that means two samples must belong to the two different classes. If they are nearest neighbors to each other, then you can say that Tomek link exists. And from that Tomek link, you have to remove the majority classes. So this is the Tomek link oversampling, undersampling. Here you see this is the original data set. Again, these blue dots, right? This represents the majority classes. These orange squares, this represents the minority classes. So what you have to do, you have to identify these Tomek links, right? So if you use the Euclidean distance, right, as the how close the two points are each other, right? So depending upon the Euclidean distance, suppose we are getting, these are the Tomek links. So 3, 3, 6 to 8 Tomek links we are getting here. So if you observe, in each Tomek link, there are two instances which belongs to the two different classes, right? So here also two, one from majority, one from minority. So in every Tomek link, if you observe, two samples are there belonging to two different classes. So what you have to do, once you have identified the Tomek links, you have to, as this is the undersampling approach, you have to remove the majority classes. So these blue color dots you are removing, right? So somewhat the data set is balanced, right? So this process you have to repeat until your data set is balanced. So as we have seen in the undersampling approach, right, what happens? So as we are removing some of the samples or some of the records, some valuable information may miss, right? So in order to overcome that problem, right, we can use the oversampling approach. So it's the synthetic minority oversampling technique. So what happens? We are doing the oversampling, random oversampling also we are doing, right? So duplicate records we are generating there. So whatever your minority samples are there, duplicate minority samples we are adding into the data set. So same records we are adding, right? So in order to overcome that problem, what will happen? Here we'll generate the synthetic minority samples into the minority class, right? So we'll not use the original minority samples. We'll generate some synthetic data or artificial data from the minority samples. So this is your synthetic minority oversampling technique. Right? So this technique, it generates synthetic data from the minority class. So same data we are not duplicating, we are generating the synthetic data. So how it works? It works by randomly picking a point from the minority class, right? And computing the k nearest neighbors for this point. Randomly, you can pick any point from the minority class. Then you can use the Euclidean distance, right, to find out the k nearest neighbor for this point. So synthetic points you have to add between this chosen minority sample and its neighbors, right? Some linear interpolation you have to do between the minority class, whatever you have chosen, and between its neighbors. So how it synthesizes? It synthesizes the new minority instances between the existing minority instances without generating the same, without adding the same minority samples into the data set. It synthesizes new instances, but that are the minority instances. Okay, so it generates the virtual training records by the linear interpolation of the minority class. So these synthetic training records are generated by randomly selecting one or more of the k nearest neighbors for each example in the minority class. So we are giving right same weightage to each minority samples in the minority class. So how this algorithm, what we have to do for doing this synthetic minority oversampling? Step one, right? We have to set the minority class set. Suppose that is the A. So for each sample belong to the minority class set A, capital A, we find out the k nearest neighbors of the X. So how to find out this k nearest neighbors? You have to calculate the Euclidean distance between X and every other sample in the set A. Right? So whichever you are getting the k nearest neighbor, k value you have to fix. And that is a user defined value. You have to fix that value. So you got the k nearest neighbors of that point. Next, what you have to do? So how many minority samples you have to generate, right? So that can be determined by the sampling rate. So the sampling rate n is set according to the imbalance proportion present in your data set. So how many majority samples are there? How many minority samples are there? By using, right, depending upon those two values, you can set your sampling rate. Then what you have to do? For each X belonging to the minority class A, n examples are randomly selected from its k nearest neighbors. It depends upon the sampling rate. Those many nearest neighbor samples you have to select, and now they will construct the set A1. Right? Now you have to do the interpolation between this current class X and the neighbors present in the set A1. Right? So for each example xk belongs to the A1 because these are the neighboring points you have selected and you have kept in a set A1, right? So what you have to do, this linear interpolation you have to use, that is the with respect to X, now you have to add one new point, right? Synthetic, you have synthesizing one new point, right? So for with respect to X, the new point is X dash. So X dash equals to the old point is X, right? Or the sample plus you generate a random number in the range 0 to 1, rand 0 to 1 into your absolute difference between X and Xk, right? If you use this one, you will generate a new sample X dash, right? So now X and X dash, right? Both are different. So this overcomes the problem, whatever we are doing in the what you call your random oversampling, right? Simply duplicate records we are adding, right? Here we are not adding the duplicate records. We are generating or we are synthesizing some new samples into the data set. So this is all about your synthetic minority oversampling technique. So there are other variations of this mode also, that is the boundary and synthetic minorities oversampling techniques. So there you have to consider, here you are considering all the minority classes, all the minority samples, right? But in the BEAST mode, you have to consider only the boundary minority classes. For those boundary minority classes, you have to synthesize new points into the data set, because it will create problem whenever we are having the points in the boundary, right? So in the BEAST mode and the mode, that is the difference. In the mode, we are considering all the minority samples, but in the BEAST mode, in the minority class set, right, we are considering only the boundary samples present in the minority class. And what is the demerit here also in the synthetic minority oversampling technique, right? So the diversity, whatever the samples we are generating, the diversity may be less also, right? Because sometimes it happens that the similar types of samples you may be generating. So the variance among the data set will be very low also. That may happen, right? Depends upon the data set. Next is here, this is one of the another undersampling approach, that is the near miss algorithm. So this is the undersampling approach. So what we have to do here, we have to balance the class distribution by randomly eliminating the majority class samples, right? So when instances of similar to your Tomek click, that is only minor differences there in between the Tomek click and the near miss. So when instances of two different classes are very close to each other, right, we remove the instances of the majority class to increase the space between the two classes. So due to which it helps in the classification process to prevent the problem of information loss, because we are removing some records, right? So the information loss, that problem may be eliminated, right? So what you have to do, this is also very simple algorithm. So this method first finds the distance between all instances of the majority class and the instances of the minority class, right? So here our target is to undersample the majority class. We have to remove the majority classes, right? So next what we have to do, n instances depends upon the balanced proportion, right? So then the n instances of the majority class that have the smallest distance to those in the minority class, we have to select and we have to remove those n instances. So there are different versions of this near miss algorithm. First one is in the version 1. It selects the samples of the majority class for which average distances to the k closest instances of the minority class is smallest. And in the version 2, that is the different here. Here we are considering the k closest instances. Here we are considering the k farthest instances. So it selects the samples of the majority class for which average distances to the k farthest distance of the minority class is smallest, right? So we have discussed, right, some of the undersampling approaches and SMOT, right, synthetic minority oversampling approach. And in the disadvantage of the SMOT, I told you that it may less diverse data may be generated during the oversampling approach, and we are giving same weightage to all the samples present in the data set, right? But the real scenario, it may not happen. All the data samples, right, they are different. Some of the data samples are easy to learn. Some of the data samples are very difficult to learn. So what we have to do, we have to assign some weightage to the samples in the minority class, right? So depending upon the weightage, we are going to generate or we are going to synthesize different number of instances, different number of minority instances of the sample for that data set, right? So this ADASYN, adaptive synthetic sampling approach for imbalanced learning, it uses the weighted distribution of different minority class examples, right? So how it will find the weighted distribution for the minority class examples, right? Depending upon the level of difficulty in learning, right? So ADASYN, it assigns some weight to the individual samples in the minority class, right? So more synthetic data will be generated for minority class examples that are harder to learn compared to those minority examples that are easier to learn. So first, in the minority class set, we have to identify which minority samples are easier to learn, which minority classes are harder to learn. So we have to generate more data, more samples from the harder points, right? And we have to generate less samples for the minority samples, which are very easier to learn, right? So in this way, it can assign the weights, and depending upon the weights, it can generate different number of instances for every instance present in the minority class, right? So what will happen if you do this, right? If you assign this weight, right, and if you are generating different number of samples with respect to each minority sample, as a result, The Adasin approach improves the learning process with respect to the data distribution in two ways, right? So what it will do in the first, it will reduce the bias introduced by the class imbalance, right? Because the model will be biased towards the majority classes, right? So it will reduce the bias because it is trying to balance the data set, right? Second one is adaptively shifting the classification decision boundary towards the difficult example, because first we are identifying which are the difficult samples, right, for which the machine learning is getting problem to learn, right? So that will shift the classification decision boundary for those difficult examples. Now let us see how this ADASIN works and how many points for each minority samples in the minority class we have to generate. So what is the algorithm, right? What are the calculations you have to do here? So generally, the ADASIN, right? So input, as you know, this is a imbalanced data set, right? So the training data set DTR, which suppose M samples are there, Xi, Yi, okay? Where your I varies from 1 to M, okay? Where Xi is an instances in the n-dimensional feature space, right? So the dimension of the problem is your M, okay? And sorry, n is the dimension of the feature space, M is your number of samples, and Xi, this is the input, Yi, this is the output, okay? So X, this is the n-dimensional feature space, and Y, this is the class identity label associated with Xi, right? So here we are talking about the binary classification. So here Y, this may be 0, 1, or this may be true, false, whatever, binary, positive, negative, okay? It depends upon your problem. So this is the input for our data, right? So how to apply this ADASIN approach to balance the data set? So first what we have to do, we have to count how many number of minority samples are there, how many number of majority samples are there, right? So let us assume or define MS, right? MS is the number of minority class examples. ML, this is the number of majority class examples. So always your MS, minority class sample, it should be less than equals to ML. And the summation of MS and ML, it should be the total samples or the total instances given, that is M. So MS less than equals to ML, and the sum of MS and ML, it should be equals to M, right? Then what you have to do, you have to define a threshold value, right? DTH. So for DTH, this is a preset threshold for the maximum tolerated degree of class imbalance ratio, right? So again, this presetting this threshold, it depends upon the problem domain, which problem you are solving, right? And what is the impact of this, right, imbalance on the problem, right? So that you have to identify. Again, some domain knowledge is required for that to set the threshold value. So that is assumed that is the DTH, right? Next, what you have to do, you have to calculate the degree of class imbalance, D, right? So small d, that is the degree of class imbalance, that is the ratio of number of samples belonging to the minority classes divided by number of samples belonging to the majority classes. So MS by ML. As ML is greater than MS, so always you will get the value D in the range 0 to 1, right? So this is the degree of imbalance. If D is less than DTH, because we are prefixing, right, presetting some threshold value, right? DTH, this is the threshold value. If this degree of class imbalance D is less than DTH, so that means we have to oversample. We have to add or we have to synthesize some minority class into the data set, right? So if D less than DTH, we have to do the following steps. So what it will do, so our target is to assign weights to individual minority samples in the data set, right? So for that, what we have to do, we have to calculate the number of synthetic data examples that need to be generated for the minority class, right? So this, as you know, this is the ML is the number of majority classes minus MS, this is the number of minority classes, into beta, where beta is a user defined value in the range 0 to 1. Okay, so capital G, this represents the number of synthetic data we have to generate for the minority classes. Total number of synthetic data, right? But how many synthetic data we have to generate for each minority sample, till now we don't know, right? So for that, we have to assign the weights to individual sample in the minority class, right? So here capital Z represents total number of synthetic data examples need to be generated for the minority class. Okay. Next, what you have to do in order to assign weights to individual minority samples, what you have to do for each example xi belongs to the minority class, you find the k nearest neighbors using the Euclidean distance. As we are having the n dimensional space problem is there, right? So you can find out the k nearest neighbors, and out of this k nearest neighbor, you find how many points belongs to the majority class. Okay, and calculate the ratio by using that number only, and calculate the ratio Ri equal to Si by k. So Si, this is the number of samples in the k nearest neighbor that belongs to the majority class, divided by total number of neighboring points. Suppose for a particular minority sample, we are getting 5 nearest neighbors, k value equals to 5. Okay, so out of 5 points, suppose 3 belongs to the majority class, 2 belongs to the minority class, right? So here the ratio Ri will be 3 by 5 because Si value is 3. Okay? Once you have found the Ri, that is the ratio of all the samples, individual samples in the minority class, then you have to normalize this ratio as Ri dash. So Ri dash, that is the weightage. What is the weightage you are assigning to that minority sample? Ith sample, right? Ri means for the ith sample, you are determining the ratio. This Ri dash, this is the weightage of the ith sample in the minority class. How to find out? So this equals to Ri divided by summation of the ratio values of all the minority instances in the minority class, right? So always you will get the value in the range 0 to 1 again here. Okay, so where Ri dash is a density distribution, or you can call this is the weightage you are assigning to the minority samples in the minority class. So once you got this weightage for the individual minority samples, what you have to do, you have to calculate how many number of synthetic data need to be generated for each minority example. Previously, we have calculated the capital G, that is the total number of synthetic data we have to generate for all the samples in the minority class. Now, for individual minority samples, how many synthetic data you have to generate. So that depends upon the weightage of that, what you call weightage of the minority sample. So that will be GI. Okay, GI means for the ith minority sample, how many number of synthetic data you have to generate. So GI equals to Ri dash, that is the weightage of the ith sample into G. G is the total number of synthetic data we have to generate. So if the weightage is more, right, that means more number of synthetic data we have to generate. So weightage is more, what it means? It means that sample is harder to learn by the machine learning model, right? So this is the GI formula. GI equals to Ri dash into G, capital G. So that it calculates how many number of synthetic data examples you have to generate for each minority class. Okay. Next, what you have to, now you know this many GI number of data we have to synthesize, right? So what you have to do here, again, some linear interpolation you have to do to generate this GI synthetic data. So for each minority data class data example xi, you have to generate GI synthetic data examples using the following steps. So I have to do, you randomly choose one minority data example xzi from the k nearest neighbors from each xi, right? Then use the simple linear interpolation, new point, new synthetic data Si with respect to the ith minority sample, right? This equals to xi, whatever value for the data point you are choosing, plus xzi, this is the minority sample from the k nearest neighbor you are selecting, minus xi, the original point, into alpha, where alpha follows the uniform distribution in the range 0 to 1, right? So if you apply this procedure, right, you can generate a GI number of or GI number of synthesized data you are able to add into the data set for the minority sample I, right? So this overcomes the problem of the SMOT, right, where you are giving equal weightage to all the samples, but here we are finding, right, we are detecting how many samples are harder to learn, how many samples are easy to learn by using this weightage calculation, and depending upon the weightage, we are generating more number of synthetic data for those minority samples which are harder to learn, right? So in this way, if you apply the ADASIN, right, this is oversampling approach, it will also solve your class imbalance problem. That means your data set will be balanced and you can use that data set for your machine learning model training. Right? So these are some of the basic imbalance learning approaches I told, some of the undersampling and oversampling. So generally oversampling, right, because we are having a small data set, we have to use this oversampling approach to solve this problem. So there are other oversampling methods and imbalances there. Your chromosome theory of inheritance also used for balancing. So if time permits, I will discuss that one also. Then there is weighted centroid based imbalance learning approaches there. So you can explore those learning algorithms, right? Imbalance learning algorithms to balance your data set. Now I will see how this class imbalancing techniques, right? Whatever this oversampling and undersampling, how it increases the performance of the machine learning model. Right? Now we'll discuss those things. Right? What are the parameters we have to consider to verify what is the impact of this imbalance learning approach on the data set, right? So the performance metric, I think already this metrics are already discussed, I assume. So accuracy, whenever you are handling with the imbalanced data set, so accuracy is not the best metric, right? Because we already discussed, right? Because your overall accuracy you are getting good due to your model is biased towards the majority classes, right? So don't use the accuracy in case of your imbalanced data set. And from the confusion matrix, right, you are having the different parameters. You can determine your precision, recall, F1 score, AUC, right, or area under ROC curve. Those things you can also use. So precision, as you know, this is a measure of a classifier's exactness, or you can call this is the how many positive classes are predicted with respect to total positive classes predicted by the model, right? Those you can call that is the classifier's exactness. You can use recall, that the measure of a classifier's completeness. That means how many positive classes are predicted correctly, right? That you have to use. That can also you can use. And F1 score, that is the weighted average of precision and recall, right? You can use 2 into, so F1 score, you can use 2 into precision into recall divided by precision plus recall. You can use this measure also. And generally, whenever you are having the class imbalance issue, you can use this metric, performance metric for comparison among different models, area under ROC curve or the AUC curve. It represents the likelihood of the model distinguishing observations from two classes. So what it represents the AUC, the true positive rate versus the false positive rate, right? So this is the measurement of the ability of a classifier to distinguish between the classes, because it compares the true positive rate versus the false positive rate. TPR versus FPR, true positive rate versus false positive rate. So how you have to interpret depending upon this AUC value, the higher the AUC, the better the performance of the model and distinguishing between the positive and the negative classes, right? So when the AUC value, it will always come in the range 0 to 1, right? When AUC equals to 1, what you have to interpret, that means your classifier is able to perfectly distinguish between all the positive and the negative class points correctly. Okay, when AUC equals to 0, that is just the reverse, and the classifier would be predicting all the negative classes as positive and all the positive classes as negative, right? So what will happen if you get, right, the AUC value in the range 0.5 to 1, there is a chance that, high chance that the classifier will be able to distinguish between the positive class values from the negative class values. So why this is happening? Because the classifier is able to detect more number of true positives and the true negatives than the false negatives and the false positives, right? So always the value should be in the range 0.5 to 1, right? If this AUC equals to 1, that is 0.5, that is another interpretation. So here we can assume that the classifier is not able to distinguish between the positive and the negative class points. What it means, either the classifier is predicting random class or constant class for all the data points. So always, if the AUC value is coming in the range 0.5 to 1, right, in that way you can interpret that our model is performing better. So higher the AUC value of a classifier, I mean the range should be 0.5 to 1, the better its ability to distinguish between the positive and the negative classes. So you can use this AUC value to compare, right? What is the right? What is the improvement in the AUC value if you use the unbalanced data or the imbalanced data, and if you apply some sampling techniques, right? How it is affecting on the performance of the model with respect to this AUC, right? So we'll see one demo or one problem we'll consider here, and we'll see what is the imbalance problem here and how to tackle this imbalance problem, and we'll see how one machine learning model will consider, and we'll see how the machine learning model performance is improving, right, if you use this imbalance learning approach. So this is one of the case study I'm going to discuss with this with respect to software engineering, that is the early software reliability prediction, designing of the early software reliability prediction model. So what is this problem? Let me discuss about only, then I will not take more time, only 4-5 minutes to discuss this problem. Then we'll see the data set and we'll see how the imbalance issue is coming and how to overcome that problem, so that the performance of the machine learning model will increase, right? So as you know, right, in the software development, right, we are having some software development life cycle phases are there, right? So this reliability means the probability of the non-failure of the software. What is the probability that the software will not failure with respect to a particular period of time, right? So that is the reliability prediction. So reliability prediction during the early phases of software development life cycle, that is before the testing phase, whatever you are doing, that is called your early software reliability prediction. Before testing phase, whatever you are doing, so here your early term will come, right? So what is the meaning here? So before testing phase, we don't have the failure data, right? We don't have the failure data with respect to the software. So we are having some software metrics during the early phases of software development process. I mean, in the feasibility analysis, requirement analysis, design analysis, right? Coding phase, some of the metrics will be available. So by using those matrices, now how to predict this reliability, right? So this, why we are doing this reliability prediction? Maybe they are generally used to evaluate the design feasibility of the software. You have to compare different design alternative of the software. You have to identify some potential failure areas in the software, right? There is a track to improve the reliability of the software, right? You can identify how much cost is required to develop the software at an early stage, and you can provide some optimal development strategy during the development process. So for those purposes, we have to solve this problem. We have to predict the software reliability during the early phases of the software. Now I will say what is the problem here. So there are different types of prediction models are there. So we're having the fault role model prediction is there, right? Defect prediction is there, development effort prediction is there, testing effort prediction is there. So we are going to discuss only one this problem, software fault flow model prediction, because I have to link with this with respect to your class imbalance issue. Okay, so here what is the problem? Fault flow model prediction means we are having right software is having a number of modules. Each module is having some metric values. So those metrics values or those metrics are called the attributes of the data set, and depending upon these attribute values of these metric values, we are going to determine whether that module is a faulty module or not faulty module. This is a binary classification problem, right? So this problem we are going to consider here, and we'll see what are the available data set for this problem and how to apply one machine learning model to solve this problem. So here this is a classification problem. Next, your software defect prediction. We have to, depending upon some metrics of the module, we have to predict how many defects are there in that module, right? That is a regression problem, defect prediction. Again, the development effort prediction means how much effort is required to develop the software, right? So with respect to manpower, or with respect to time, with respect to cost, we can determine. Again, 3 different scenarios are there. Last one is software testing effort prediction. Again, how much effort is required to test the software. Again, it may be manpower, time, cost, whatever, different parameters are there, right? So we'll see what is this first problem, the software fault prone model prediction model. And simply we use your artificial neural network model to solve this problem. Right? So as you knew, so the need for the software fault prone model is that. So what is our target? Our target is to predict the software fault prone modules during the early phases of software development process. Right? So what is this benefit? It will help the software project managers for proper planning, for the better testing activities, right? So the testing efforts are focused to the most troublesome fault-prone modules only, instead of focusing all the modules of the software system. So once we have identified out of the 1,000 software modules, suppose 200 modules are only faulty modules and the remaining 800 are non-fault-prone modules, right? So more testing effort we can assign to the faulty modules only, instead of assigning to the all the 1,000 modules. We'll focus or we'll assign the testing efforts to the 200 modules only, right? So to achieve the high software reliability in the lesser time, so it is important that the testing should be prioritized. We have to give priority to the testing based on the fault proneness of module. So this is the need why we are solving this problem. This is the importance of the problem. For this purpose, we have to solve this problem. Right now, we'll see what are the attributes present here, right? In order to define the fault proneness of a software module, what are the attributes required or what are the metrics required? So there are a number of software quality metrics, right, which are considered or which are affecting the faultiness or the fault proneness of a software module. Okay. So generally, they are classified into 5 major categories. Your lines of code, right? LOC, you know the KLOC, right? LOC, Halstead matrix, your number of operators, operands, unique operators, operands, derived Halstead matrix, your using the unique number of operators, operands, right? There are your design complexity, essential complexity. Those are your derived Halstead matrix, and branch count, right? Your branch count may be your cyclomatic complexity, you know, right? How many branches are there in your software, right? By using those metrics, right, we can predict whether the module is a faulty module or not faulty, right? So how to solve this now? We are assuming we are having a number of metrics are there for a module, software module, and by using these metrics values, we are going to predict whether this module is a faulty module or not faulty module, right? So let us assume we'll use simple the artificial neural network model to solve this problem, right? So we will discuss this ANN approach, artificial neural network approach, to predict the fault-prone modules in the software. Right. So this problem is your software fault-prone module classification problem, right? So this is using for classifying the modules into faulty modules or not faulty modules, binary classification, right? So what is this advantage? It ranks the software modules according to the number of defects, right? And thus it can be used to determine the order in which the code should be inspected, right? Whenever you will debug, right? That in that order you have to debug. Okay. So developer can allocate the limited test resources to the code areas that most likely contain the bugs. So what is this benefit? As already we have discussed in the previous slides also, it reduces the overall cost of maintenance activities and maximizing the company profits. Now, how to solve this problem by using this basic ANN approach, right? So what is our problem statement here? Our problem statement is we have to develop an artificial neural network model to classify the software modules into faulty and not faulty, right? So this is a binary classification problem. There are two classes, faulty or not faulty, or 0, 1 or positive, negative, right? Whatever the way you want to try interpret. So here I will use 0 for not faulty, 1 for faulty, right? So what we are doing here, the model for software fault-prone classification. So we have to do this mapping. Y is the target, whether this is a faulty or not faulty. So y equals to function of m, right? So m is the given module, small m, this is the given module having number of matrix values, right? So this function is unknown here. If you know the function, right, which function you have to apply on these models, then you can get this y value. So this function y or this mapping, so this function f or this mapping f, we can determine by using this artificial neural network model, right? So this y equals to f of m. This is the statement here. So here m is the given module and capital Y is the output. What is the class of that module, whether it's a faulty module or non-faulty module. So it can take two possible values, either 0 or 1. 0 means this is the software module is not faulty. 1 means the software module is faulty. Okay. So what is the representation of this module name? Now the software module M is represented as a set of software metrics. That means these are the attributes. Suppose n dimensional problem, this is, or n number of features are there, or n number of software metrics are there. So M is represented by software metric M1, SM1, SM2 up to SMN. So n number of features or n number of software metrics or n number of attributes are there. Right? So what is our target? Our target is to find the approximation to the mapping F using the ANN approach. So what is this mapping? That we have to find out, right? So how to do this one? So generally the ANN approach or the any machine learning approach, this is the procedure you have to follow. We are having this data set, right? So our data set is software metrics data sets, right? So for individual module, what you call the software metric values are given. So we have divided the data into two parts. First, suppose we are partitioning the data into suppose 70-30. 70% data we are using for training, 30% data we are using for testing. Right? So this is the training data, this is the testing data. So what we are doing in the training phase? So after the training data, we have partitioned the data into training and testing. We have to pre-process the data. So under the pre-process, right, we have discussed some outlier analysis and the class imbalance issue, right? So you have to verify those procedures you have to follow, and you have to check whether you can identifying any outlier in the data set. If outliers are there, how to handle those outliers, and if any class imbalance issue is there, how to handle this class imbalance issue. So those things you have to do here in the pre-process part. Okay. Next, the pre-process data you have to take as the input or consider as the input for the machine learning model. So here we are using the ANN model. So any other model also you can use here, right? Now once your model is trained, so you have to train your machine learning model, and I think some of the machine learning algorithms, how the training happens, maybe it is discussed, so I'm not going in that direction. So assume the ANN model we have trained by using the standard backpropagation algorithm. Right? Now, once our model is trained, what we have to do now, we are having the 30% testing data is here, right? Again, the testing data also you have to pre-process, right? And that pre-processed data you have to provide to the trained model, right? So the trained model, what it will do, that function F, right? So this mapping F, this will be determined by the training of the N, right? So to the trained model, if you provide the test data, will generate the output y equals to f, because that f will be determined by using the trained model, right? So now y equals to this model we are providing, new model we are providing to test. So f of m, right, f will be determined by the trained model, and m is the model we are giving as the test. Now it will generate y value, whether this is 0 or 1. So 0 means not faulty, 1 means faulty we are interpreting, right? So similarly, so this is the predicting phase. So training phase, we are training the machine learning model, and the predicting phase, we are testing the machine learning model, the trained model, right? Once the model is trained, how it is behaving on the unknown data. So this is the standard approach we are following, right? So I will show you on the data set, and I will show you the Python code, right? How it helps in improving the machine learning performance here, right? Now see in the CM1 dataset, so this is the software project, right? So with respect to some modules are there, some of the matrices are there, and their values are there, right? So we'll use this CM1 dataset to evaluate the performance of the machine learning model by using some of the imbalance learning approaches, right? So these are the some of the metrics available in the dataset, right? So these are the different LOC, right? Lines of code, cyclomatic complexity, essential complexity, design complexity, right? Number of operators, operands, volume, right? Program length, difficulty, intelligence. So these are the some of the metrics related to the software engineering. So I am not going detail towards these attributes or toward the metrics. So the metrics can be anything, right? It may be different for your problem domain. So assume these are the attributes, n number of attributes present in the data set, and y, right? So output is whether the module is faulty or not faulty, 0 or 1, right? So how to solve this problem by using this simple ANN algorithm, right? So we have to pre-process the data first, right? Once we have divided the data into training and the testing, so we have to pre-process the data. So here I am using the natural logarithmic transformation, right? So as we have seen in the outlier concept, also some transformation at the end we have seen, right? How to prevent the outliers in the data set. So natural logarithmic transformation. So what it will do, it will convert the data distribution from highly skewed region less skewed region. Okay. Then you can do the normalization, mean max normalization to transfer the data value, right, high ranges into a small range. These things you can do for the data processing. Again, it depends upon your data set, right? What is there in the data set, how much variance is there, how much difference is there in your each attribute values. Right? Next, once you have pre-processed the data, next you have to train the ANN model or any machine learning model, right? So here we are using the ANN machine learning model. So we have to find out what is the architecture of the ANN, right? What is the training, how much data you have to use for train, how much data you have to use for testing, and how you are going to train your model, right? So for that, first you have to determine the ANN architecture. ANN architecture means what you have to do, you have to define how many layers are there, right? As you know, we are having only one input layer and one output layer in the artificial neural network, right? But the number of hidden layers you can change, right? And the number of input layer is one, number of output layer is one. And next, how many number of neurons in each layer, right? So number of neurons in the input layer and the number of neurons in the output layer, it depends upon the problem, which problem you are solving. Suppose here we are having n dimension or n number of attributes are there. So the number of input neurons in the input layer is n, that is the dimension or the number of attributes, right? And the number of neurons in the output layer is how many outputs you want. Here only we want the whether this is faulty or not faulty, one output, right? So one neuron is sufficient in the output layer to solve this problem, right? Next, once you have determined this ANN architecture, number of layers and the number of neurons in each layer, and the hidden layers, right, you have to follow some procedure for the hidden layer. You have to do some optimization or some heat and trial method also you can do. Next, what you have to do, you have to identify the activation function of each layer. How each layer and each neuron in each layer, they are converting the input into the output, that you have to consider here. Right? There are some log sigmoid, sigmoid, tan sigmoid, linear, linear rectified, linear unit, right? LU. Different types of activation functions are there. So depending upon your problem, right, you identify some of the activation functions and you can use those activation functions for each layer. Or you can right, you can assign different activation function to each neuron in each layer also, right? Next, what you have to do, you have to train the model using your standard backpropagation algorithm, or you can write your own algorithm. You can customize the training algorithm, right? You can use an optimization algorithm to train your model also, because your target is to optimize the error, right? How much training error your target is to minimize that one. So you can go for the standard backpropagation or you can customize your training algorithm, right? Once your model is trained, now what you have to do, you have to test your model using the testing data. Now once you are using testing your data, I told you the different performance measures, right? So those measures you can use to test the accuracy of your model. And generally for the class invariance issue, I told you, you can use the AUC, right? So this is the some of the standard, some architecture I am using here: input layer, hidden layer. This is the output layer. These are the some of the activation function, log sigmoid activation function. No, I am using, and how right? You know, I assume all of you know the standard, right, working procedure of the ANN model and how the backpropagation model works, training algorithm works, how it will backpropagate error towards the output layer to hidden layer one, hidden layer one to hidden layer two, right? Then once the model is trained, now you provide this n number of attribute values for a new module into the trained model. Right? Now what it will do, it will provide the zi or the y equals to either 0 or 1. Right? So in this way, you can solve this problem by using this ANN model. Now let me show some Python implementation of this problem, right? And we can see only one or two simple imbalanced learning approach or the oversampling approach, and we will see how it is affecting the performance of this ANN model. If you are having any doubt up to this, please ask me. Just wait for 2-3 minutes because I have to open the Python code. Okay. Now let us see. So this is the data set, this CM1 data set I told you. So what is there in this data set? There are 37 attributes are there. Okay. You see these are this first row, LOC blank, right? Branch count. So these are the 37 matrices or 37, n value is 37. These are attributes are there up to this. And the last column, this is the whether the module is defective or non-defective. So if you see the last column, right, many of the entries are 0. If you see 0, 1. So 0 we are using for, right, not faulty, 1 for faulty, right. So there are, so for each attribute the values are given, right. If you see the ranges of the attribute values are different. Somewhere it will see this 1, 5, 16. Somewhere you see this is the 1633. Here 3670. Here you see the range for this T column. Right? The ranges are varying from one attribute to another attribute. That's why we have to do those transformation, right? So how many rows are there? So here in this data set, we are having around 327, maybe 327 data point rows or instances are there, or the modules are there. So 37 attributes are there, 327 instances are there, and this is if you see, if you observe this last column, there is a class imbalance issue here. As this is a binary classification problem, here the imbalance problem is there, right? So let us see how to solve this problem by using ANN, and we will see some simple sampling algorithm, oversampling algorithm, and we will see how the performance of the model is increasing if you use this imbalance learning approach. Okay. So what we have to do? Again, I'm assuming you have some knowledge in the Python code also. So whatever, right, you have to import all the required, here you see the smooth, random oversampler, borderline smooth, ADASIN, everything is there, right? So if you want to write your own, right, own oversampling approach, you have to write the code for this. But these are the libraries present here. Okay. These are the undersampling, your near miss, random undersampler, all are here. Okay. Then what you have to do, as you are using the ANN model, right? So you have to import that for the necessary things for the ANN model also here, right? So this is the pandas, so NumPy, right? Math, then your model selection, right? Import train test split. So we are using the test split criteria to divide the data into this much percentage of training, that much percent of testing, right? Then cross validation score for measuring the training, right? How much, how the model is trained, right? Then we are using the pre-processing as the standard scaler. Standard scaler means your Z score we are determining, right? For detecting or for handling the outlier here. Okay. Then your classification report, as this is a classification problem, you have to import this make scorer classification report, confusion matrix, accuracy, precision, recall, those are there. Okay. Then this is a sequential model. So we are input layer, output hidden layer, output layer, one by one sequence we will add, right? Then these are the activation functions, your dense dropout activations we are importing. Then here your what is the optimizer, right? What is the optimizer? SGD, your gradient descent optimizer we are using for training the neural network. Okay, then we are importing some pipeline to plot some things, right? Then you import, you read the data set. So this is the CM1 data set we are reading, right? Because I have shown you. Then this is the scaler. You have to identify which are the inputs, which are the outputs. Okay. So for 5 iterations, I am training the network here. Okay. So assume, so I am focusing on this AUC only. We'll see how this AUC is increasing if you use the imbalance learning approach. Okay. So what you have to do here, now for 5 iterations, you have to train, right, your network. So your X train, Y train, Y train, Y test. This is the splitting you have to do here. So here test size equals to 0.3. That means 30% you are using for testing, 70% you are using for training. Then the sequential model, you have imported this one, right? Sequential. So model is your sequential. Then you have to add the what you have to add? You have to add the layers. How many layers, how many neurons you have to add here, right? So this portion is for adding the input layer, hidden layer, and the output layer. Okay. Then what you have to do? You have to use that optimizer to train your data set. So here binary cross entropy is used as the loss function, and Adam optimizer you are using to train the network, right? Then what you have to do? You have to fit the model, right? X train, Y train for epochs 20 epochs you are doing this one. Then where you are predicting, predicting the model, right? For the X test data, we have divided the data into 70% and 30%. Okay. Next, right? So these values, so depending upon the confusion matrix, you can write the formula for calculating the AUC you will get directly, right? So I am focusing on AUC only. There are other parameters also you can see. 2 positive rate, 2 negative rate, right? For false positive, right? So those things, G mean, so many parameters are there. So I am focusing on AUC only. So AUC value you have to calculate. So before sampling, how many non-defective samples are there will print. After the before sampling, how many defective samples are there we'll see, and what is the false positive ratio or recall. So I will print only this AUC value. Our target is to AUC value, right? So if you see this AUC, so these things we are printing, we are applying the ANN model to solve the problem with the imbalanced data only, because we have observed there are many zero instances than one, right? So majority classes are non-faulty and the minority classes are faulty. So up to this, we are doing with this imbalanced data, original data, we are training the ANN model and we are testing and we are printing the AUC value, assume the AUC value. The other measures are there, we'll see on the AUC, right? Next, what you have to do, again, you assign those values, initialize to 0, and what you do, you apply some sampling technique here. So here, simply the random oversampler I have used, so you can use other sampling techniques also here, right? Because all are important. So you can use those sampling and you can balance the data set. And same thing you do. Again, you partition the data into training and testing. Again, you call the sequential model. You add the input layer, hidden layer, and output layer, right? Then you use the optimizer to train the network, right? Binary cross entropy used for loss function. Again, you train the model. Once the model is trained, you test with the new data set, right? The 30% data set. Once you have provided the test data to the trained model, again you from the confusion matrix you calculate these parameters. Suppose this is the AUC, right? So after sampling, we'll see how many samples are there, defective samples are there, non-defective samples are there, and what is the AUC value. So we'll see whether there is improvement in the AUC value or not. That is our target, right? So how much improvement? Again, you have to do so many things here, because here in the simple program, I have not done the normalization or transformation. I have not done anything. Only the standard scalar is used, right? So you can improve the AUC value by doing other things also here, right? This is only to show only what is the impact of the sampling approach on the imbalanced data whenever you are using the machine learning approach, right? So if you see before sampling, right? Before sampling, this is the AUC. AUC is 0.51, right? And here the number of defective sample and the non-defective samples are varying here, 228, right? AUC value is 0.51. And if you do the simple oversampling, random oversampling, now you see the non-defective sample, this is 198, this is 199, because somewhere I have fixed the right, imbalance proportion also I have fixed somewhere. That's why this is coming 198, 198, same number of instances it is generating. So if you see here the AUC, so previously we have seen the AUC value equals to 0.51. Here we are getting the AUC value is 0.62, right? So you can see there is a significant improvement only if you are using the changing the imbalanced data into balanced data by using the random oversampler, right? So you can check for the SMOT, right? You can check for the ADASIN, and there are other imbalance learning approaches also here. So time is there, so I will tell you another imbalance learning approach, right? So that is, for that there is no library is there in the Python. You have to implement those algorithms and you have to balance your data set, right? So from here we can observe that there is a significant improvement in the AUC value for the problem, right? by using the ANN as the classifier to solve this problem. And there is some found that some imbalanced data is there. We have applied the random oversampling approach, and the AUC value there is improvement from 0.51 to 0.62. Right, so you can verify with other things. Right. So one of the other imbalance learning approach, I will tell you, I will take just another 10 minutes to complete that one, right? So this is the how this chromosomal theory of inheritance is used to right, generate your oversampling. This is generally oversampling approach, right? Like your SMOD, ADASIN, what we have seen whenever we are generating or doing the linear interpolation. So it is observed that the data, whatever the samples we are generating or synthesizing, those are very less diversity, right? So less diverse data we are generating. So in order to generate higher diversity data, we can use this chromosomal theory of inheritance so that we can get right good performance measures from the machine learning models. Right. So what is this chromosomal theory of inheritance? Right. So for generating higher diversity data, and this is your oversampling approach, chromosomal theory of inheritance can be used. So what is this chromosomal theory of inheritance? As you know, according to elementary biology and the genetics, right? Genes we are studying, right? The basic unit of hereditary. These are located on the chromosomes. And they are passed on to children in equal amount with half from both parents during their fertilization. Right? So this theory is known as the chromosomal theory of inheritance. This is a old theory, right? Proposed in 1902 by Walter Sutton, right? So what this theory states that new offspring receive 50% of chromosomes from other parent, thereby making the new offspring similar to both parents and at the same time unique from both parents. So this is the general theory, right? Genetic theory also says this one, right? So here what is the new offspring means? Your new samples, new minority samples you have to generate, right? Because this is the oversampling approach I told you. So some new minority samples we have to generate and we have to add to the data set. So those new synthesized generated minority samples are called your offspring, right? So they will receive 50% of chromosomes from each parent. Each parent means for both classes, right? For this is for the binary classification only. And thereby making the new offspring, they are similar to both parents because 50% they are getting the data, right? And at the same time, this is unique from both parents. So this diversity will be generated in the minority sample if you apply this chromosomal theory of inheritance. So this theory has been used to propose a new oversampling approach, and that is called your Muhakkil approach, right? So generally the advantage of the chromosomal theory of inheritance sampling approach is that whenever we are using SMOD, B-SMOD or ADASIN, right, result in over-generalization, that is the higher rate of false alarm, right? And it will generate near duplicated data instances. That is the less diverse data. So if you apply this chromosomal theory of inheritance, the diversity among the instances will be high. So which will lead to improve the performance of the machine learning model. So this algorithm, this is the Muhakkil approach. So that in that reference that paper, and you can see how that algorithm works, right? So what it will do, it will interpret two distinct subclasses as the parents, right? As I told you here, suppose the majority class, minority class, they will treat as the parent and they will generate a new instance, right? That inherits different traits from each parent and contributes the diversity within the data distribution. So how this works, now if you see this diagram, you can understand. Suppose S1 is the majority class, S2 is the minority class. So what we are doing, S1 and S2 we are combining and we are generating an offspring C01, right? So how to generate that offspring? For that some methodology you have to follow. Once this child offspring is produced, the next level what we will do from S1 and S2. Next level. C1 to C11 we have to produce. If our data is not balanced, then we have to go for the next level. If the level 0, our data is not balanced, we have to go to the level 1. In the level 1, you see C12, this is generated from C01 as well as from S1. That means it is inheriting the chromosome or the genes from its parent and its ancestor. Right? Similarly, C11, it is generating the genes from C01 and S2. Again, after this level 1, after the generation of the level 1 samples, right, that is the minority samples, still your data set is not balanced, you can go for the level 2. In the level 2, now you see C24. This is inheriting the property of this one as well as this one. Similarly, this 2, 3. This is inheriting the property of this one, this one. C22, again, both parents, right? C21, both parents, right? So what is happening now? There is a borderline, right, from the parents here, the S1 and S2. Whatever data you are generating for the different levels with respect to n levels, your data, whatever samples you are generating, they are coming within this range, S1 and S2 range, right? But what is the advantage here? Your data, right? Your higher diversity data, you can generate by using this chromosome theory of inheritance. So generally, there are 3 phases in this approach. One is your diversity measurement, first phase. Second phase, you have to partition the data and you have to pair the data. This pairing, right? This diversity management you have to do in the first phase. Second phase, you have to pair the data. You have to partition the data and you have to pair the data. Third phase, you have to synthetic sample, you have to generate, right? So this algorithm, you can see this is a very simple algorithm because more number of steps are there, right? So you have to go thoroughly to this paper for understanding this algorithm, right? So here, suppose we are having a binary classification problem. We are having a data set of minority and the majority class samples, right? So this is the p-value, this is the balanced, how much data, right, you want for the imbalanced proportion is there. So output is your balanced data set at a set PFE value. The PFE value means that is the imbalanced proportion, okay. So what you have to do, you have to split the data into 2 classes, minority class and the majority class, n mean and the n majority, right? Because these will form the parents here in this diagram, if you see, this S1 and S2, right? So n mean and n major. Then you have to do, you have to compute the number of additional minority classes you have to generate. So what is that minority classes you have to generate? So whatever n major minus n mean, right? Suppose majority classes are 200, minority classes are 50. So 200 minus 50, 150 minority instances you have to generate. So that total number of majority and the minority samples will be same, right? So to compute the number of additional minority classes to be generated, that is the RL length n minimum. Okay, then what you have to do, X new is the new samples you are storing in the next new. Okay, they are your whatever new samples you are generating, you are storing there, right? And this X new K, that is, it is keeping count of how many synthetic samples you have generated, because you have to generate K number of minority instances, right? So here, what you have to do, you have to partition the data into 2 parts, right? So for that, this is a Mahalanobis distance is used, right? That is the depending upon the covariance matrix. This is the formula for calculating the distance, d square equal to x minus mu, inverse covariance matrix of x minus mu, right? Then what you have to do, all the data samples, you are calculating this distance, then you are arranging the data samples in the decreasing order of this distance, right? Then what you have to do, you have to find the midpoint or the middle distance, okay? Then you have to partition the data up to the mid, like your binary search, right? 1 to mid, then mid plus 1 to n. You have now, you got the 2 partition. Now the first partition will become the parent one, second partition will become the parent two. Now you got the boundary of the parent one and the parent two. Now how this will be calculated? You have to take a point from this one, you have to take a point from this one. Then you have to take the mean on that value or the average of that value. So that will generate a new sample, right? So that is the phase 1 here. Okay. So this is the same thing at the 8 point I told you. So you have partitioning the data into 2 parts, n1 to n mid, then n mid plus 1 to total k number of points, right? Then for each bin or each part, you have to, what you have to call, you have to sequentially assign the unique level cell I from I to mid, right? Then for what you have to do, you have to select 2 instances from bin 1 and bin 2, I mean parent 1 and parent 2, where levels of YA, YB are same. Levels should be same, right? Then what you have to do, you have to generate a minority class synthetic sample by taking the average. So this is the new upstream you are adding. Okay, so now add x to x new and increment x new. So this is the step for your this offscreen generation. Then you have to count whether this many number of minority instances you have generated or not. Level wise I told you, right? If you have not generated, then you have to go to the, you have to repeat these steps, right? By using this diagram I told you, right? It has to go to its parent and ancestors also. So those are these steps from 8 to 10 you have to follow, right? It repeats 10 to 12 to create the two different sets again by using the sum systems, right? So whenever your x new set, the count of the x new, this is greater than equal to t, you can assign all samples with the x new with the level of the minority class, because our target is to do the oversampling with the minority classes. So now we have generated t number of minority instances into the data set. So what benefit you will get here if you are generating or you are doing the oversampling by using this technique, whatever data the minority samples you are generating, all the diverse data. And the diversity is high, right? The distance between the data points are high. So it will help in proper training of the machine learning model, so that you will get better performance measure for the machine learning models with respect to your problem, right? So you can go through this paper so that you can understand how this algorithm works. 1 minute. So this is the reference I have given here. 1 minute. Just give me 1 minute. So these are the references you can see. These are some of the good algorithms for the oversampling approach. So that Mahakil algorithm explained diversity-based oversampling approach, right, to alleviate the class imbalance issue. So this has been used for the disruptor defect prediction problem, right? So you can see whether this imbalance learning approach can help you to solve your problem. Then there are other data and algorithm hybrid approach for imbalance data problems in the deep neural network. So you can see this algorithm also. So how they can be used to balance the data and how it is affecting the performance of the machine learning model. So this is all about your outlier concept and the class imbalance issue in the machine learning problems. If you are having any questions, you can ask.